Okay, I think we are ready to start the morning session. And it's a pleasure to introduce Konstantin Zarembo, the first speaker of today. And he will speak about integrable D-branes and one-point functions. Please.
I'll talk about the work with Charlotte Christensen and Dean Longwu. And it has to do with one-point functions in the presence of D-branes. So if you have a D-brane, then a string, it's just a surface in space-time where the string can end. Basically, it's just boundary conditions imposed on the string. And they can be Dirichlet and Neumann in perpendicular and longitudinal directions. Or they can be D-brane can be magnetized, which simply means that the boundary conditions are mixed, Dirichlet, Neumann. So these boundary conditions, in general, will break integrability of the ambient string. But in some instances, they do not, and these are precisely the cases we are interested in. So if they break integrability, then we basically can do nothing, because scattering on the D-brane, or so that the magnet propagating along the string will not only reflect from the boundary, but it will also create particles, and this will produce a mess, and so we will not be able to solve the model. But if integrability is preserved, the scattering is elastic, and moreover, for integrability to work, it has to be consistent with the bulk scattering. So the reflection of the brane should satisfy certain conditions that are express consistency with the bulk scattering of excitations of the string. So then, in such a situation, we can define a partition function. So now this is a partition function on a half-infinite cylinder. That's the simplest object we can compute in the presence of the boundary. And well, we can take the limit where the cylinder is well, literally half infinite, so very large. And the partition function then will have an exponential factor that scales with the length of the cylinder. And so this will be just the same free energy that characterizes closed string. But then there will be a prefactor that's known as G function, or boundary entropy. And the nice thing about it is that it is calculable, systematically calculable by thermodynamic Bethe-Ansatz. So it's as calculable as the bulk free energy. So in Adscft, well, the string being infinite means that it goes down to the boundary. So what we are considering is a string that ends on the D-brane, or begins on the D-brane, then propagates in ADS, and then it approaches some point on the boundary. So this means that we are studying a correlation function of a single insertion. So it's a condensate. So in the presence of the D-brane, local operators develop condensates, and the condensate is described by this process. So a string emitted from the boundary and then disappearing in nowhere because it can be absorbed by a D-brane. So the D-brane can, so integrable D-branes were actually classified by Decalinoz in 2011. And they can have different shapes. So D-brane can go parallel to the boundary. That will describe Coulomb branch, as where the gauge symmetry is Higgs. It can have one leg on the boundary and then go to infinity. So this would correspond to a defect inserted in the boundary. So we'll be dealing with a defect CFT. Or it can have both legs on the boundaries. So this would correspond to insertion of some very heavy operators. And if you're considering a string on top, then this would probe these two operators. So we'll be dealing with a three-point function. But I'll concentrate on the second case where the D-brane describes a defect in conformal field theory. So what does it correspond to in the field theory context? A d-brane is a classical object, so in string theory it's just fixed, it cannot move. Likewise in field theory it is described by some classical field configuration. So if you have an operator, and let's say we are at very weak coupling, at zero coupling, then to the leading order we can just substitute this classical solution in the operator, and that would give the leading order of the correlation function. So in the spin chain interpretation, this immediately maps the problem to computing an overlap of whatever state characterizes the operator with a new state that isn't used by the d-brane, and which is obtained by simply multiplying the classical fields and taking the trace. So this is the type of objects I'll concentrate on. And there are two basic examples of integrable theory, n equals 4 and the BGM. I'll talk about the latter one. So it's a three-dimensional theory, just reminding you how it looks like, with Lagrangian that contains two Chern-Simons terms for two types of gauge fields, which come with opposite signs and a common coefficient that has to be quantized. And then on top of that, there is matter in bifundamental representation, which contains both bosons and fermions, and the theory is actually supersymmetric if the coupling constants are adjusted appropriately. And it has a well-defined Hooft expansion, which is the expansion in the inverse of the Chern-Simons level. So the coupling constant is the ratio of number of colors to the level. And it is known to be integrable. So what kind of defects exist in this theory? Well, we will be looking at the domain wall defects, so they are codimension 1. And they better preserve some symmetries. And particularly if you want to preserve supersymmetry, they should have zero energy in some sense, or smallest possible energy with given boundary conditions. And basically solitons that are supersymmetric, they always satisfy equations that are first order, not second order in derivatives. So the action then can be written as a total square plus some boundary terms. It always happens like that. So BPS monopoles, instantons are of this type. And here too one can write this horrible Lagrangian that I showed in the previous slide. It can be written as a total square, but only if we restrict the fields so originally there were 4 fields because the global symmetry of ABGM is SU4. But if we say that 2 of them are equal to 0, then the Lagrangian or the energy, static energy of the remaining 2 fields can be written as a total square. So one needs to use some identities that are only valid where the group SU4 is broken to SU2. Once the energy is written in this way, we know that the lowest energy configurations should be such that this modulus squared is 0. And these configurations are automatically supersymmetric, like anything supersymmetric in a given sector has 0 energy. So the BPS domain walls are such that they satisfy this condition. So we get the first order equations, nonlinear, so they're cubic equations, and in principle not easy to solve. But nicely, these equations can be written in the form that appeared many times before, and in particular in n equals 4 superyoung meals. So if we write the equations for composite fields, namely for a bilinear of the original scalars, then we can expand them in Pauli matrices. So because the indices alpha and beta run from 1 to 2, and it's natural to decompose them in the basis of Pauli matrices. So then the simple calculation shows that equations for the coefficients are nothing but NUM equations, which are very, very famous in mathematical physics. In particular, they arise in n equals 4 superyoung meals when we describe the supersymmetric domain walls. So basically, the domain wall in a BGM is mathematically the same as in n equals 4, but you need to find appropriate variables. So the simplest solution is, well, these equations don't have smooth solutions. There should be, they have to have poles in X. And the simplest solution has just a single pole. So the fields simply decay as 1 over X and go to infinity at the position of the domain wall. Then for the coefficients, we get just algebraic equations. And these algebraic equations are simply commutation relations of SU2. So the solutions are characterized by embedding of SU2 in the color group of the original theory. So SU2 has well, many representations. So so the solution will be then characterized by the dimension of this representation, which will be Q minus 1 dimensional. So if one multiplies fields in the opposite order, one can show that, well, again, the same exercise shows that the coefficients are representation matrices of SU2. And this representation will be Q-dimensional. So one can also write an explicit formula for the original Y variables, and this solution was found by Terashima in 2008. And what it describes is a domain wall, so that the fields are, they depend only on one coordinate. So on one side, one should, so the fields go to infinity on the domain wall, on the position of the domain wall. So on one side, they have to be declared infinite. So they simply disappear from the spectrum. And on the other side, they relax to 0. So this is a domain wall that breaks original symmetry by Q and Q minus 1 units. So the classical fields have this block shape of the size Q minus 1 times Q. Well, this is the starting point of describing this domain wall. So at leading order in perturbation theory, this is just a classical solution. The ADS dual that describes this at strong coupling is also known. It is a D-brane configuration, which, well, in ADS, this is a codimension 1 D-brane. So it intersects the boundary at one point. Well, I mean, pictorially it's 1 point, but in fact it's a domain wall, so it's 1 plus 1 dimensional. And then it extends in the bulk and becomes an ADS3 embedded in ADS4 at an angle alpha that in fact is related to this parameter Q well, it's just the number of units by which the gauge symmetry is broken. So On IDS, the D-brane wraps a two-dimensional cycle, and so well, and CP3 has natural non-contractible cycles, so that there is a two-dimensional sphere that is topologically non-trivial. So one can wrap a D-brane along the sphere, and then it is also pierced by Q units of magnetic flux. So this defines the boundary conditions for the sigma model. They can be shown to be supersymmetric, but they are also integrable. This was, in fact, this is not in the classification list of Dekel and Oz, but George Leonardopoulos showed that this D-brane is also integrable, and so we expect it to be such at weak coupling as well. So at weak coupling, the theory is described by a spin chain, and for a BGM, this spin chain is of the Vegov-Inarovich type. So the fields are bifundamental, so one has to alternate them. And so the spin chain is naturally alternates sides with representation of SU4 and its complex conjugate. And for alternating spin chains, the natural Hamiltonian is contains interactions of three sides, not just nearest neighbors. And so this, if you do perturbative calculation at the leading order, you find that the dilatation operator is precisely the Hamiltonian of this integrable type. So if you consider one such operator, and it will be described by beta ansatz, now this SU4 spin chain. So to compute the one-point function, we just substitute the classical fields for the field operators. And so this way, the one-point function will be expressed as an overlap of some boundary state in the spin chain and the beta eigenstate that describes the operator. And so this boundary state turns out to be very, very special in this, that it also preserves integrability. So let me explain, well, how this state looks like and what it means for a state in the spin chain to preserve integrability. So this state will be of the matrix product type. So the fields that we use to construct it, they have three indices. So two of them are color indices and one is flavor. So they have, well, color indices run from 1 to n. But in the classical solutions, the field is restricted to a block of size q minus 1 times q. So these indices will run either from 1 to q minus 1 or from 1 to q. And the flavor index is just a fundamental representation of SU4 or its conjugate. So the fields will then alternate between S and S dagger, and then the color space will form an auxiliary space from the spin chain point of view with the bond dimension that also alternates between q minus 1 and q. So matrix product states of this type are known to be integrable. For instance, in N equals 4, there is a set of integrable boundary states that are of matrix product type. So we may expect that this state will be also integrable. So to show this, it's more convenient to use this representation with the composite fields, where we sort of combine two sides into one. And then bond dimension is either q dimension or q minus 1 dimension. And this representation also makes connection to group theory immediately, because the matrices that describe the state in the auxiliary space are simply representation matrices of SU2. So the simplest case is, so they are characterized by either Q minus 1 dimensional representation of SU2 or by Q dimensional representation. And the simplest case is when this representation is trivial. So the smallest value of Q is 2. And then one representation is, well, defining representation of SU2, and the other representation is one-dimensional, meaning that it's trivial. So in that case, the state is even simpler. So there is no trace to take because the representation is one-dimensional. And so what we get is a valence bond state, which projects the indices into SU2 singlet. So we take two sides, which are representations of dimension 4 and its conjugate, and we so project it onto the subspace where indices can take two values, and also onto a singlet between the nearest neighbor sides. So and then one can show directly that this state is integrable. And well, let me explain into words what it means for a state to be integrable. Now, if you have a boundary in an integrable, well, spin chain or field theory, it doesn't really matter. This boundary will preserve integrability if scattering is elastic and is consistent with the bulk matrix. So then if we do rotation by 90 degrees, so the boundary becomes space-like, and then time runs along the cylinder. So this property of elastic scattering means that particles, so the state will create particles, right? So it's from nothing. And for integrability to hold, these particles have to come in pairs with opposite momenta. This is the basic property of an integrable state. Basically, the state will be integrable if magnons appear in pairs. So the states are parity invariant, and well, with some work, one can show that the state that appears from the D-brane in the ABGM satisfies this property. So it only has non-trivial projections on beta eigenstates, which contain all magnons in pairs. So what we want to do now is to compute an overlap of the state with a given beta state, and this will give the value of the condensate of the corresponding gauge theory operator. So the beta eigenstate will be characterized by a set of 3 types of beta roots. So it's the beta equations are of standard Lie algebra type for SU4. So the question is how to compute the overlap of a beta state with this given state that preserves integrability. So this boundary state is not an eigenstate of the Hamiltonian, but integrability guarantees that it has some nice properties. And in particular, the overlaps of this type of states with beta eigenstates were found to have very constrained form, and just by experimenting with many examples, it was shown that they always follow the same pattern. So first of all, there are some selection rules that follow from obvious symmetries. So one symmetry is this reflection Z2, that's a hallmark of integrability, and here this Z2 acts in a bit non-trivial way on the Dynkin diagram, so it not only reflects the rapidities, but it also interchanges the Dynkin labels. So it's in terminology in this field, this state is called achiral. So there is the parity symmetry. It changes the sign of auxiliary roots, and then it interchanges momentum carrying roots and also changes their sign. So the state is also invariant under SU2 cross SU2 subgroup of SU4. So at the level of highest weight, it is equivalent to SU4 symmetry. So only singlets of SU4 will have non-trivial overlaps. So the beta states are highest weights. And if you are computing an overlap of a highest weight, then it will be non-trivial only if the number of beta roots are equal on all nodes, and this is the condition that the beta state is a singlet. And then it's, well, known in many examples that the overlaps of this type of states have a concise determinant representation. So the state is characterized by a reflection matrix. So, well, in the simplest case, it's just reflection phase. So the non-trivial part of this overlap formula is a determinant of the Gadan matrix, but well, in this case, it is not just a determinant, it's a super determinant. And super here refers not that to the original supersymmetry of a BGM, but to this fake supersymmetry related to reflection Z2 invariance. So once we have Z2 invariance, we can define super trace and therefore a super determinant. Well, the Gadan matrix is just the Jacobian of beta equations. So this factor is basically universal, so it doesn't depend on the model. It is constructed using symmetries. And it's only this prefactor that is model specific, and it does depend on the boundary state and is, well, physically it is constructed from the scattering phases of magnons on the boundary. Now this formula is, well, there is no, well, I guess it should be possible to derive it from TBA, and this was done in some examples by Caetano and Komatsu. But originally it was derived example by example. So in the Heisenberg model, one can construct boundary states that are integrable. So with a lot of work, one can compute an overlap, and then one finds this formula. And then in some examples it was conjectured, in some it was proven, but it always has this, this form. And so this BGM boundary state associated with the domain wall is no exception. The formula is again of this type. So the nested equations are, well, here they are a very standard type. So one just needs to compute then the Gadan matrix. Its superdeterminant actually can be factorized, so one can diagonalize the Z2 symmetry. And then superdeterminant is just a ratio of two ordinary determinants, and can be written in, well, in very explicit way. So the overlap formula was actually, well, known. It was derived by Gombar, well, it can be written either through, well, it contains superdeterminant and then product of some Q functions of the spin chain, and they simply come about from the scattering phases of magnons that interact with the defect. So here, in this example, the Q functions, only the Q functions of auxiliary roots appears. And you can see that this Q function, so that there are two Q functions in the denominator under the square root, and one is the outside. This will have certain significance when we will supersymmetrize this formula. So anyway, this formula was derived, and we can just use it to write down the expression for the one-point function. So the one-point function in the present of the defect has this nice determinant representation, which was generalized by Christensen and Gomberg to the case of this generic matrix product state. So in that case, it contains a sum of terms of this type, and this is easy to understand qualitatively. So the state has the form of the matrix product state, so it's like a character in some auxiliary space, which is a representation of space of SU2. So the overlap will also be of character type. So the basic structure of the superdeterminant will be a common factor, and then there will be something, some prefactor under the square root. But the Q functions that stand outside, they instead of a single Q function, we will have a sum of Q functions, and this precise formula was found in this very recent paper by Charlotte and Tomasz. Now to extend this condensate formula to all possible operators, we need to include fermions, derivatives, and field strengths, so all possible operators that one can imagine. So doing this directly is a very complicated story, because you need to do a computation that goes beyond two loops, so that fermions do not appear, and they don't have classical expectation values. Then gauge fields are also not switched on, so one would need to make a very complicated calculation. But symmetries allow one to circumvent this direct computation and just guess the formula from consistency conditions. So we know that to extend the dilatation operator to other sectors, one doesn't need to do an extra calculation of diagrams. So the bit equations are just one just adds a few nodes to the Dynkin diagram to make it supersymmetric, and this will describe all possible operators of the theory. So in this case, the symmetry group is OSP64. So here is the Dynkin diagram. So it has three nodes that describe SU4, and then one add two nodes that make a fermion out of scalars, and then two fermions are equivalent to a derivative, and then one extra node flips the spin, the space-time spin of the field. So since this is the symmetry group is a supergroup, in fact, this diagram is not unique, so that one can write down many Dynkin diagrams that describe OSP4, and there is a symmetry of beta equations that allow one to go from one diagram to another. So this is known as fermionic duality. Basically, one of the QQ equations transforms the diagram to a different grading. So if we start with, if we have fermion node, then we can replace beta roots on this node by their duals using the QQ equation. If one re-express the beta equations for other roots in terms of this dual fermion roots, then the nodes next to this root, to this original node, will also become fermionic. And so there is a very systematic procedure how to transform the beta equations between different gradings. So what is less well known, but it is also true, is that the superdeterminant is the Godin matrix also transforms nicely. But, I don't know what happens to its determinant, but if one computes superdeterminant, then it basically remains the same up to some factors that are simply Q functions of the spin chain. It's plus or minus 1, right? So the off-diagonal elements of the Cartan matrix are plus 1s or minus 1s. So solid line is minus 1, dashed line is plus 1. Sorry?
In principle, it's all fixed by the Deacon diagram.
Yes, yes, of course. This how this dashed lines and solid lines alternate, it is prescribed from the beginning. So it follows a very systematic pattern. But I prefer to draw different lines for plus and minus 1. Just an imitation. Yes. So anyway, then, and the superdeterminant is the most complicated part of the formula. So, so this means that if we know how to write the formula, the overlap in one representation of the Dynkin diagram, we can go to other possible representations by simply doing this transformation that would produce some Jacobian. But since this, well, the formula we expect it to be of the same form for all gradings, it should produce, so this Jacobian shouldn't spoil the form of the overlap. So it should always remain of this type. So there is a product of Q functions under the square root. And the Jacobian should cancel some of these Q functions, produce new ones, but it shouldn't spoil the form of this formula. And this turns out to be a very, very strong condition, so that allows to extend the overlap from SU4 to the whole diagram without doing any calculations. So if we write it in this notation, so these labels now are simply the arguments of the Q functions in the, or how many? So in the, it's arguments of the Q functions in the overlap formula. Then fermionic duality simply, well, first of all, the formula will transform nicely if there is a fermionic Q function evaluated at 0. So if it's in the numerator, then after the duality transformation, it will appear in denominator, and then there will be Q functions on the neighboring nodes that will appear arise from the Jacobian. And the same holds for the inverse transformation, where the Q function at 0 appears in the denominator. So these are the basic rules that we are allowed to follow. And the structure is so rigid that it is enough to know how what the Q functions are in this corner of the diagram. So the rest is fixed by the consistency conditions. So it is only possible to go between these three diagrams if the Q functions that appear in these two additional nodes follow this particular pattern. And so we can write overlaps for all possible operators and also in all possible gradings. In particular, we can write it in the distinguished grading where the fermionic and bosonic nodes alternate. And this is the form of the Dynkin diagram that can be extended to high loops. Like there is a Gromov-Yerry equations which describe the overlap for, that describe asymptotic beta equations. So what we expect is that this formula is basically the same at higher loops. If we, instead of Q functions, write replace them, basically replace U variables by x plus and x minus. Okay, so I come to my conclusions. You can just read them. Thank you for attention.
Thank you very much. Questions?
Can you extend this construction for all loop, not just tree level?
More or less. I think that this formula should, properly understood, should be the extension to all loops. But well, one needs to be careful of how to replace Q functions by, this one loop Q functions with the exact Q functions. This is in principle ambiguous, and the explicit formula has not been written, but I think it's a matter of doing some extra checks to.
Okay. One more question.
Thanks for the very nice talk. So, if I understand you've got the one-point functions of any operator with this boundary state.
Yes.
Written down, and so in principle, you could sum over all these states, all these one-point states, right?
Why would they want to do it?
So one thing that would be nice to calculate, I don't know if it's at all possible, would be to calculate the cylinder diagram. So an exchange between two such boundary states. And that exchange is literally just a whole bunch of one-point functions, right? It's just, it goes to some...
So you want to insert two domain walls?
Yeah, exactly. And we know, or at least we know in say, flat space or other simple backgrounds that that whole cylinder diagram is really just, you know, a bulk state propagating.
Yes. So in this case, well, I mean, this domain walls, they're all BPS, so they shouldn't interact. So in principle, the string diagram between 2D branes should cancel. How to think about it in field theory, I'm not sure, but I have to think about it.
It's
but
true,
it's a very
it would
question.
cancel, yes, but you might want to separate it out into let's say, the graviton type contributions and the Ramon type contributions.
Yes.
I guess what I'm getting at is there are some nice theta functions that appear usually, and I'm wondering if you are inventing in this way generalizations of theta functions.
I haven't thought about that, but definitely it's an interesting question to see how the difference interact.
Okay, one more question from here.
Does this formula have some this strong coupling-like limit, which reminds something from group theory, like Clebsch-Gordan coefficient, or?
A strong coupling.
Yeah, as in the old days we compared this fake strong coupling expansion from perturbation theory with real strong coupling expansion from.
So here it can only be done at the level of BMN, basic BMN string. So it can be done, but for some reasons it has only been done for the string that's point-like and which is the ground state of the spin chain. So for which the formula is basically trivial. So, well, I mean, it's trivial up to prefactor. So this prefactor can be reproduced. For spinning strings, explicit string calculation is not very simple. It's not very simple to construct this solution of the string that starts at the boundary, expands, and then ends on the D-brane.
So there is nothing to compare with if you do this fake strong coupling expansion. You remember that one can.
Yes, there is nothing to compare with, just because the technicalities have not been overcome. So no one constructed this solution, but they do exist, and in principle, it's a meaningful calculation that potentially one can do, but no one has done.
Thanks.
Okay. Are there any more questions? Okay. If not, let's thank the speaker once more. And I think we can reconvene as originally planned at 10:15. Yeah. I think we are ready to continue the morning session. And our next speaker is Shota Komatsu, who will talk about cross-cap states, integrability, and holography. So, please.
All right, so thank you, and let me thank the organizers, and it's great to be back to Budapest again. So yes, today I'm going to talk about integrability and cross-cap states, which is based on the joint work with Joel Caetano, who is at CERN, and also work in progress with Joel Caetano, and Leonardo Rastelli, who is in Stony Brook, and Paolo Soresina, who was a student of Luca Gurigolo and is now visiting CERN for 10 months. And I should also mention that there was also a nice related paper by Tomas last week, and also this morning by Ekman. Okay, so let me start right away by saying what is cross-cap. So the cross-cap state has been studied a lot in 2D conformal field theory in the past. So in that context, the cross-cap state is defined as the following, in the following way. So you first take the flat complex plane, and then do the identification, z is equal to -1 over z bar. So this identification maps the exterior of the unit circle and the interior of the unit circle. And at the boundary, which is on the unit circle, you do the antipodal identification of points. So after you do this identification, the fundamental domain can be taken to be the exterior of the unit circle. And you can alternatively view this configuration from the point of view of radial quantization, and especially from the exterior point of view. Then you can view it as some kind of a non-trivial state created by this weird boundary condition. So in some sense, it's a kind of weird version of the boundary state. And as a result of inserting this cross-cap state, so this is a typical notation for the cross-cap state. As a result of inserting the cross-cap state, the surface becomes non-orientable, and you can, for example, get Klein bottle or Möbius strip. Okay? So let me just say the punchline of the talk. So the punchline of the talk is that integrability, so the goal of my talk is to study cross-cap states in massive integrable field theory, not in 2D CFT, as was done in the past. So the punchline is that integrability survives in the presence of cross-caps. And furthermore, the overlaps between the cross-cap state and an excited state in integrable massive quantum field theory and also the spin chain can be computed analytically, and you can have some analytic formula for that. And furthermore, they compute one-point functions in n equals 4 supermills on real projective space, RP4, with charge conjugation. And there are also byproducts that we got from the analysis, but I don't have time to mention that. So this is the plan of the talk. So let me first start by explaining why studying cross-cap is interesting. But before talking about the cross-cap, let me first talk about something related, which is boundary. So in the past, the boundaries in 1+1 dimensional systems have attracted much attention. And one of the most successful examples is the Kondo problem, which is basically the following statement. So if you take some metal like gold and then experimentally measure the resistivity, then in the experiment, people observe that resistivity actually goes up. So this is what's called anomalous resistivity at low temperature. And Kondo basically pointed out you can understand this behavior by the following model, which is the free fermion plus magnetic impurity. And this magnetic impurity, he pointed out that is important for explaining this anomalous resistivity. And so this model by itself is 3+1 dimensional. But if you focus on the S-wave scattering of free fermion, you can do the dimensional reduction and then map it to 1+1 dimensional fermion with boundary. And furthermore, this system can be solvable by integrability or CFT, and they're having a lot of progress on this topic. And let me also just say that the same kind of physics also governs the famous Kallen-Rubakov effect, which is about scattering of electron against monopole. And from high energy point of view, also the boundaries in 1+1 dimensional system is important because we know that the 2D CFT with boundary is related to D-branes in string theory, as Kostya explained in the previous talk. And more recently, there have been a lot of literature on the boundary state in CFD and spin chain, because you can use it as the initial state for the quantum quench problem. And even more recently, these boundaries in 1+1 dimensional system made appearance in n equals 4 supermills, as Kostya explained, for example, in the analysis of defect 1-point function and determinant 3-point functions. So now, let's move on to the cross-cap. So in 2D CFD, there exists another important class of states. That is called the cross-cap state. And this system is, the cross-cap is important for analyzing 2D system on non-orientable surfaces like Klein bottle and Möbius strip, that, as I mentioned earlier. And also, it's also important in the analysis of 2+1 dimensional SPT phase with time reversal symmetry. So, but to me, more important motivation is to understand orientifold in string theory and also string compactifications. So one crucial difference between D-branes and what's called orientifold is that orientifold can have negative tension. And using that property, you can actually use it to construct DS vacua in string theory, and that kind of allows us to evade the no-go theorem, the famous no-go theorem by Maldacena and Nunes. However, if you look at the cross-cap, if you try to understand the cross-cap in massive field theory, especially in integrable field theories and spin chain, you discover that there is almost no literature for that. And that is the gap that I want to fill in my talk. And as we will see, the cross-cap states in spin chain provide new integrable initial states for quench protocol. And it has interesting properties like long-range entanglement and the volume law of the entanglement entropy. And furthermore, the analysis in n equals 4 supermill suggests a new class of defects in general higher dimensional conformal field theory, which I would call orientifold defects. And I'm going to explain that as well. Okay. So now let's talk about the cross-cap overlap in integrable field theory. I'm going to explain how to compute it. So the basic setup is this picture, which is the cylinder whose endpoints are capped off by two cross-cap states. Although it might not be obvious, this is topologically same as the Klein bottle. So let's analyze this Klein bottle partition function in two different ways. So the first way to analyze this partition function is to expand in what's called tree-channel expansion, which is to basically insert a complete set of state here and viewing R as a time direction. And if you do this expansion, you can express this partition function in the following way. So you have the overlap between cross-cap and the energy eigenstate square, and then there is a propagation factor coming from this propagation of distance R. And in particular, if you take the limit where R goes to infinity, you can project this sum to this contribution from the ground state, because the ground state dominates the answer. So this is basically telling us that if you compute the partition function of the Klein bottle and take R going to infinity limit, you can read off the cross-cap overlap as the prefactor. So let's go to the other expansion. So this is more interesting and complicated, which is called loop channel expansion. So in the loop channel, I want to view this L as time. But because of the cross-cap states, it's actually a little bit more complicated than the boundary case. So let's talk about a constant time slice, which I denoted by red line. So this constant time slice, let's start from here and then goes all the way to here. Then, because of the cross-cap identification, you have to continue the constant time slice to here. And then you can continue here and here, and then comes back to the original point. So this is basically telling you that the constant time slice is defined on the volume 2R, not R. So another peculiar feature is that if you take this red line and time evolve by L/2, then you get this dashed line. And this dashed line is at the same position as this red line, so you are basically taking some kind of a trace. But as the arrow, directions of the arrow indicates, you see that the directions of the arrows are opposite. which basically means that you need to insert a parity operator before taking a trace. So in the loop channel expansion, what this means is that you get this kind of trace, which is like a trace of the system whose system size is 2r, and then you time evolve by minus L/2, and then insert the parity operator. And if you write explicitly this trace using the eigenstate of the parity, then you get this kind of expression where this epsilon is basically the parity eigenvalue, which is -1 or +1. So far, the discussion has been quite general, but we know that in integrable field series, states are labeled by the rapidities of particles or excitations or magnons. In that case, by analyzing how parity operator acts on the rapidities, you can argue that this sum can be converted into this sum, which is basically sum over parity invariant solutions to the beta equation. So this is basically the effect of the parity operator insertion. And by equating the loop expansion and the tree expansion, you finally get this formula. So you do the sum over parity invariant solutions to the beta equation, and then take the limit r going to infinity. Then you can read off this cross-gap overlap as the prefactor of this exponential factor. So if you look at the left-hand side, then you can see that this is almost of the form of thermodynamic beta ansatz. The only difference is that we need to deal with these parity constraints because we are restricting the sum of the states to be the parity invariant states. So basically, we just need to understand how to deal with the parity constraints. So let's talk about it. So this is the expression that I had in the previous slide. And in order to deal with that, I will take the most direct approach, just write down the beta ansatz equation. And in this case, we need to be a little bit careful because the beta ansatz equation takes slightly different form depending on whether you have a zero momentum state or not. So if you don't have any zero momentum state, the beta ansatz equation for parity invariant states take this form. On the other hand, if you have a zero momentum excitation, then the equation takes this form. And now comes the crucial observation. So the crucial observation is that these equations are formally identical to the beta ansatz equation in the presence of boundary. So in the presence of boundary, people know that the beta ansatz equation take this form, where R is the reflection amplitude, which depends on the details of the boundary condition. If you compare this, and then you immediately notice that if you replace RP squared with SP minus P, then you get the equation for this sector, which I call S sector. And if you replace RP squared with this combination of S matrix, then you get this T sector. So this is basically telling you that once you do this identification, we can just recycle the result for the boundary problem, which was already solved by thanks to many people actually in the audience, and also including people not in the audience. Okay, so this is a review of the solution to the boundary problem. This is actually something Kostya already mentioned. So the idea is to now consider the cylinder with a boundary and then analyze this partition function in two different ways and solve it using thermodynamic beta ansatz. I'm not going to explain you how to derive this, but the final result takes this form, which is complicated. But the important point is that final result consists of two factors. So the first factor is some integral of y functions. And the second factor is a ratio of Fredholm determinants. But this Fredholm determinants is a little bit complicated than what you encounter in other contexts because the weight factor inside the Fredholm determinants depends on y function, which by itself is a solution to this nonlinear TBA equation. And furthermore, what's important for the application to the cross-gap state is the following fact. So the only dependence on the details of the boundary state sits here, the factor theta. And as you can see, this is the only place you see the dependence on R of u, which is the reflection amplitude. And furthermore, you see immediately that if you replace this R of U by some S matrix, which is needed in order to apply this formula to cross-cap state, then you see some nice cancellation between this factor and this factor. So this is already telling you that something nice happens if you apply this formula to the cross-cap state. And this is the final result. So this one comes from the S sector, and this ratio of Y function comes from the T sector. So the analysis is straightforward, but it's a bit complicated, so I'm going to skip it and just show you the final result. And again, this is the standard ratio of Fredholm determinant, which is identical to the one that I showed here. And so this is the prediction for the overlap for the ground state. But once you have a result for the ground state, you can also have the result for excited state, thanks to the two people in the audience, Patrick and Roberto. And basically, you just need to do some analytic continuation. And as a result of analytic continuation, you get some modified Fredholm determinant, which now the Fredholm determinants also contain some kind of like a summation piece in addition to integrals. And once you get this excited state result, then you can also analyze the asymptotic limit in which the volume becomes infinite. And then you can see that in the asymptotic limit, this integral just disappears. And then you are left with this summation part. And by rewriting this, analyzing this summation part, you realize that you can actually rewrite it into a finite dimensional determinant, and which very much looks like a golden determinant. But which is kind of formula Kostya already showed you. But one important difference is that here, I just have a ratio of determinant, nothing else. So in this sense, you can view this cross-cap overlap as some kind of simplest possible G function, at least mathematically. So this is a check we did. So we basically took what's called staircase model. So this is a very interesting model proposed by Zamolodchikov. We don't know the Lagrangian, but it is known that if you take this S matrix and then compute the ground state energy, then it shows a series of plateau, and the values at plateau exactly coincides with the central charges of unitary minimal models, which basically says that this model actually goes through all, comes close to all the fixed point of those unitary minimal models, and flows in the IR to a massive phase. So we just took this model and applied this formula. And again, we saw that also the cross-cap overlap exhibits a series of plateau. And if you compute the values at plateau, then it exactly reproduces the cross-cap overlap for the A-series minimal models for the ground state, and which we also computed using the modular S matrix using the CFD technique, and they both basically agree perfectly. Okay, so this was the story for the integrable field theory. Now let me just explain how to define cross-cap states in integrable spin chains. So again, before talking about the cross-caps, let me go back to boundaries in spin chain. So there are two boundaries people discussed in the context of spin chain. The first is basically open spin chain, which corresponds to putting boundaries in space. So this is something people have been analyzing since the 80s. And there have been a lot of works about the integrability of open spin chain. However, what's more relevant to my story is what's called boundary states, which people started to explore about 10 years ago, I think. So this is some particular state in closed spin chain, and this is the analog of the boundary state in quantum field theory. And in the case of XXX spin chain, it takes this form. So you basically first form an entangled pair of nearest neighbor two sites, and then let's call it K of J, and then you just take a tensor product. So because it's defined in this way, this is almost a product state, and first of all defined almost locally, much like a boundary state in field theory. And the next important property is that it is short-range entangled, just because it's a product state of entangled pair of nearest neighboring spin sites. And because of this, it provides you an ideal initial state for the studying time evolution of entanglement. And in addition, people discovered that there is a simple formula for integrable spin chain, which is basically ratio of determinant and some prefactors. And now let's ask how to define a cross-gap state in spin chain. So basically, as I mentioned in the beginning, the cross-gap state can be defined by doing the antipodal identification. So the naive guess is to construct some kind of entangled pair of spin chain sides which are antipodally related, and then take a tensor product. And unlike the boundary state that I discussed earlier, which is basically entangled pair of the nearest neighboring sides, this cross-gap state is long-range entangled. So if you, for example, compute the subsystem entanglement entropy and plot it as a function of lengths, then so this grows linearly until the subsystem size reaches half the system size, and then it starts decaying linearly. And whereas if you take a boundary state, it exhibits like this. So the entanglement entropy is always very small. And this blue line is a kind of typical entanglement scaling for high energy, highly excited state. And furthermore, you can actually show that this particular state, in the case of XXX spin chain, is annihilated by infinitely many conserved charges, which are generated by the transfer matrix T of u minus T of minus u. So this basically guarantees the integrability of this cross-gap state. And furthermore, we also computed the overlap between the cross-gap state and the beta eigenstate using Mathematica. And we found numerically, without a proof, that they admit a very simple determinant formula, which is basically similar to the formula that I derived from the quantum field theory. And again, the important point is that it is just given by ratio of determinant, nothing else. And so, as I mentioned, this coincides with the asymptotic limit of the overlap formula for integrable QFTs. And it's similar to, but simpler than, the overlap formula for the spin chain boundary states. And I should also mention that this formula, we didn't provide a proof, but it was proven very recently, actually last week, by Tamas in a very nice paper. Okay, so this is basically telling you that having this analytic expression potentially allows us to compute some like a time evolution of this state, cross-gap state, and maybe it provides us a new tractable initial condition for quantum quench, which is quite different physically from the boundary state because it's long-range entangled. So let me finally talk about how to relate this cross-gap state to n equals 4 super-MLs. So this is a work in progress with Joao Caetano, Leonardo Rastelli, and Paolo Sorresina. How much time do I have? Sorry? 18? 18, okay, that's too much. Okay, so, all right, so let's go slowly. So the claim is the following. The cross-gap overlaps on the worksheet compute the one-point function in n equals 4 super-MLs on real projective space with charge conjugation. I'm going to explain what I mean by charge conjugation. So let me first explain what do I mean by real projective space. So the real projective space RP4 is in a sense like a 4-dimensional version of the cross-gap. So you basically take R4 and perform this identification. Then as a result, the fundamental domain is exterior of this unit sphere, and you get some non-orientable space, which is RP4. And you can actually analyze correlation functions on RP4 and also write down some crossing equation. So if you consider a correlation function of local operator on RP4, there is a new conformal data which is basically one-point function on RP4. So because RP4 identification breaks part of the conformal symmetry, one-point function of local operator is now non-zero. And the crossing equation schematically takes this form. So let's take, okay, actually here I'm taking the fundamental domain to be interior. but that's okay. So you take like a two operators, and there are like two different ways to perform the OP of these two operators. One is to kind of like do the OP directly by approaching two operators. And another way is to approach O1 to the mirror image of O2. So this leads to the crossing equation. And importantly, unlike the boundary state, which conformal boundary condition, which basically introduces new conformal operators, which are basically operators sitting at the boundary, it doesn't introduce new operator, and basically two channels are both governed by, in some sense, bulk OP, but the cross ratio are different because in one way, like you are approaching two operators directly, whereas in the other way, you are approaching two operators using the mirror image. Yes? Oh, okay. Yeah, so, right. So let's see. Yeah, I think it's, well, yeah, well, but important point is that on the sphere, like you are doing antipodal identification. So this probably like gives you an idea how it's related to RP4. Yeah, yeah, yeah. Yeah, it's a consequence, yes. Okay, so then let's talk about, so far I was talking about the general CFT on RP4. So then let's talk about n equals 4 supermills on RP4. So in n equals 4 supermills, we can actually define a half PPS version of RP4 by combining this like a space-time identification with some Z2 identification of scalar fields, well, and also fermions, but it's complicated, so I'm not going to write it down. But if you just do this identification, it turns out the final, the resulting, if you just do this identification and compute a one-point function, you discover that this leads to non-integrable setup. There is nothing nice happening if you do the computation of one-point function. So this is the result discovered by Joao and Leonardo in the paper which appeared this year. However, we understood that there is actually small modification that leads to integrable setup. And what is that modification? So this modification is the following. So integrability gets restored if we combine this and with another Z2 symmetry, which is basically charge conjugation of SUN. So instead of doing this, I'm going to identify phi 1, 2, 3, phi 1, phi 2, phi 3 to the transposition of phi 1, phi 2, phi 3. So here, I'm using the fact that all the fields in n equals 4 supermills lives in the adjoint representation of SUN. So you can view it as a kind of n times n matrices. So this, I call it charge conjugation because I'm basically combining this identification with some kind of charge conjugation of the SUN generators. So these are, TAs are basically SUN generators. And if you do this identification, the scalar propagator on RP4 have a very interesting property. So there is one piece which corresponds to direct contraction. So this piece is just usual 1 over x minus y square, and also the like a double line notation is the usual one. So you just like connect the double lines in the usual way. But there is also a piece which is kind of like a weak contraction between the mirror images, and that gives you this factor 1 plus x dot y square. And in addition, because I'm doing this charge conjugation, if you try to write a double line notation, then you get some kind of twisted double line. And furthermore, if you want to compute a one-point function using this propagator, then you can basically ignore this part because this part is just a self-contraction which you remove when you define the local operator, because this part is also there in R4. And by defining like a local operator in R4, you basically remove the contraction coming from this part. So all you need to do is to do the contraction of one operator by itself using this propagator. Okay, And if you do that in the large N limit, you discover that the leading diagram is in some sense maximally non-planar. So you basically do the contraction of antipodal sides of the spin chain. So it's a little bit hard to see, but if you like draw some other configuration, then you can immediately see that those are subleading. So this is basically telling you that the leading large N answer is given by antipodal contraction of single trace operator, and this naturally makes connection to the cross-cap overlap that I described earlier. So, and this is a conjecture for the asymptotic one-point function. So again, the conjecture is very simple. Well, actually, I'm missing square root here, so there should be a square root here. But the important point is that the form is very similar to the one-point function in the defect or boundary problem, but the only difference is that we expect there is no extra factors. And let me just explain for those who are not familiar with this expression. So this G is given by derivatives of logarithm of beta equation, and which is often called the golden matrix. And then this S determinant is some kind of defined by defining the Z2 grading structure. And this Z2 grading structure is dictated by the problem you study. And here we are taking the same Z2 grading structure as the defect one-point function because the symmetry structure is the same. But importantly, as I said, we don't have any, we expect we don't have any non-universal prefactors. Okay, so this was a conjecture for the asymptotic one-point function. But at this point, it's still a conjecture, and we are trying to do the one-loop check. We are doing the one-loop check of this conjecture. Yes, square root is missing. Yes, thank you for point. Sorry? Because I forgot to write it. So you need square root. And so let me just mention also this new class of defects in Hardy. So one way to understand the RP4 in it is to use the embedding, what's called embedding coordinate, which embeds the R4 into 6-dimensional space with a null condition. And in terms of embedding coordinate, you can describe RP4 in this way. So you just identify x minus 1 with x minus 1 and x1, 2, 3, 4 to minus x1, 2, 3, 4. But if you phrase this problem in this way, then you wonder that there may be actually higher codimension version of RP4, which I'm just calling orientable defects. For example, we can consider something like this. So also one is identified with plus sign, and the rest is identified with minus sign. And physically, this corresponds to some kind of higher codimension version of RP4. So the questions that I want to pose are, can we define them consistently in any CFT? So if so, what are crossing equations? And furthermore, in n equals 4 supermills, I expect there should be half BPS versions of these higher codimension versions of RP4. And combined with charge conjugation, they probably lead to cross caps on the worldsheet, which preserve integrability and can be studied at finite coupling. So let me conclude. How much time do I have? 7 minutes. OK, very good. So the punchline is that the cross cap is integrable. And the overlap with the excited state can be computed in both field theory and spin chain analytically. And in some sense, it looks like a simplest possible G function. And furthermore, it's relevant for n equals 4 supermills on RP4. And we have a conjecture for the asymptotic formula at finite lambda. And we are doing one-loop checks and also SUSY localization. And so for the future directions, it's probably interesting to use this cross-cap state and study some kind of quench dynamics. And in particular, because cross-cap states is long-range entangled, it's interesting to see what happens if you start doing some kind of a measurement protocol, which performs the projective measurement. And in particular, it's probably interesting to see whether we can observe some kind of measurement-induced phase transition. And that's work in progress with condensed matter friends, Pieter and Yuan. And so far, the cross-cap overlap that I discussed, especially on the field theory side, is only for the diagonal S matrix. And it's important to generalize the derivation to non-diagonal S matrices and also theories with bound states. And I should also emphasize that this is really the best arena for developing quantum spectral curve approaches to the correlation functions, because the final formula is just given by the ratio of Fredholm determinants. So now the question is how to rewrite the Fredholm determinants in terms of quantum spectral curve. And also, it's also interesting to try to find more examples of orientifold defects in n equals 4 supermills and general CFDs. And I just wanted to mention that in the famous paper by Guyot and Witten, which studied half BPS boundary conditions in n equals 4 supermills, some of them involve O5 plane, so that might lead to some kind of nice integrable setup. And finally, it's also interesting to study the cross-cap for fishnet, which is kind of related to the talk by Eduardo we heard yesterday. And probably also for fishnet, cross-cap might be actually simpler than studying some kind of D-branes and boundary states. And another comment that I wanted to make is that in the analysis of n equals 4 supermills, I mentioned that actually the diagram that contribute to the one-point function is actually maximally non-planar in some sense. So I would expect that there might be some Yangian invariance also for non-planar diagrams if it comes from some kind of cross-cap type contractions. And that's the end of my talk. Thank you very much.
Okay. Thank you very much for this interesting talk. We have some questions.
Hi. So I didn't quite get, in the context of unequal 4 superior meals, you also have, thanks to this charge conjugation identification, some natural way in which the parity condition appears, so the fact that you probably would expect rapidities to come in pairs or to be 0.
Sorry, could you repeat the last part?
So whether you expect that thanks to this charge conjugation condition, you also get some parity condition on the rapidity.
Oh, that
like you had in the previous.
I see. So the charge conjugation on the, well, I don't have a direct connection, direct way of connecting the two, but the charge conjugation corresponds to this twisting of the double line, which basically corresponds to like changing the orientation of the string worldsheet. So, and then indeed, if you compute a cross-cap overlap, then there is a selection rule, which Kostya explained. So like only the states which are parity invariant have non-zero cross-cap. So there is an indirect connection, but I don't know how to make a direct connection.
Thank you.
Okay. More questions?
So what is the string counterpart of this orientifold theories?
Yes.
And why is it possible to see why your new orientifold, this the Wolff's transposition, is better from the point of view of integrability on the string side?
Okay, so the why transposition is better than without transposition? Okay, so actually, I didn't mention, but okay, so this is something discussed already by in the paper by Joao and Leonardo. So one important difference is that if you compute one-point function of RP4 without charge conjugation and the one-point function on RP4 with charge conjugation, then actually large N scaling is completely different. If you compute one-point function without without charge conjugation, then actually like a one-point function grows like N to some power, which basically indicates that the dual description is some kind of back-reacted geometry. And indeed, that's what they constructed in their paper. On the other hand, if you compute a one-point function with charge conjugation, and then it's order 1 in the large N limit, it basically indicates that it corresponds to some kind of probe. And indeed, our conjecture is that it corresponds to some kind of probe or one plane.
Okay. More questions?
Sorry, I probably should have read those papers you mentioned, but is it so obvious that n equals 4 really exists on RP4? I mean, you take rays in 5 dimensions, actually, right?
Mm-hmm.
And then basically every ray in 5 dimensions is a point in, you can say it's a point in RP4. So locally it looks like R4, but then you have funny boundary conditions.
Yeah,
but
yeah.
is it, for example, clear? Have people looked at that the fermions don't cause problems with this?
Okay, so for this particular setup, I think we can actually show that this whole setup preserves the BPS, half BPS boundary condition. So because of supersymmetry, I expect it's well defined.
Okay, and related to this, is this some kind of? I mean, usually super Young-Mills is defined on Minkowski space, right? So what about the signature here? And also, you wrote this inversion formula. Is it like Minkowskian inversion? Or
Actually, that's a very good point. We were working on Euclidean space. So this inversion formula is the Euclidean inversion. And actually, precisely speaking, the holographic dual is a little bit different. It's like a Euclidean ADS5 times DS5. Because in order to preserve supersymmetry on the Euclidean space, you need to kind of like change the signature in the R symmetry space.
So even the R symmetry becomes non-compact, right?
Yeah. So it's actually O1 plane. So the conjecture is that it's actually O1 plane in Euclidean ADS5 times DS5.
And then the total supersymmetry left?
That's like 1 half BPS. Yes.
Yeah. Okay. Thank you.
Okay. Anything more? Kolja?
Thanks for the nice talk. So probably stupid question. So roughly speaking, you define this absorber as having some Z2 symmetry generator and then projecting the state. So can you think about some like more general, I don't know, some if you also do some rotation at the same time when you identify, or like there could be probably many Z2s. Is there any criteria which of them would be integrable, for example?
Well, I expect like as long as it's Z2, you can basically combine it with this RP4 and cross-cap. So I think we can define like a different cross-cap states on the worldsheet for every like Y reflections of the Dinkin diagram.
But can I ask, is your cross-cap state is always bosonic somehow? Or,
Yeah, I don't have a good way to answer that, but yeah, it's probably bosonic, but yeah, I haven't thought much about it.
Okay, Bogdan.
Thanks for a very nice talk. So, since these are really orientifolds, they should have some tension. Do you know? I didn't see any minus sign appearing in your one-point functions.
Yeah, that's a good point. Actually, determining the overall minus sign is a little bit complicated because we are always starting from this Klein bottle and then taking a square root. And when you take a square root, actually, like you cannot determine the sign just by considering the Klein bottle partition function. And so the quick answer is that so far we are unable to determine the sign.
But why not just consider the Möbius strip?
Yeah, that's the way to go, yes.
And then it should be fixed, right? For each, each kind of thing,
yes, it should be fixed.
And there's a prediction for what that is.
Yeah.
Okay, we're still on time, so we can have maybe one more question. Otherwise, I can maybe ask, is there any connection to Anomalous for super Young-Mills with alternative gauge groups? I mean,
you mean SON?
SO or SP, I mean, that's normal.
Yeah, so in some, yeah, so let me just mention that, like, so this, sorry, not this one, the other way. So this identification is what converts SUN to SON or SPN. Actually, like, there should be SPN version of this, although, like, we haven't explored this. Yes. And in particular, like, coming back to the last point, I think the one way to study kind of like a cross-cap amplitude or cross-cap type Feynman diagram is to study diagrams that show up in like a SON n equals 4 super Mills or SON fishnet.
Right. one last question.
Sorry, I may have missed it, but you were talking about the long-range entanglement in the spin chain setup, and I'm wondering if you did any analysis in the field theory. I mean, regarding these boundary entropy techniques or something like that. So did you do anything like
Sorry,
that?
can you speak a bit louder?
So did you do anything about the entanglement in the field theory, because you were mentioning it for the spin chains with this page curve. So did you compute anything in the field theory?
Oh, in the field theory, you mean like entanglement property? Well, I think I expect the same, but in field theory, well, the cross-cap is a little bit singular because if you just take the overlap of the two cross-cap states, then it diverges. So we probably need to do some kind of like a time evolution in the Euclidean domain, and then like I think I expect them to have a similar behavior.
Okay, let's thank the speaker once more and move on. Okay, so let's move on. And our next speaker is Thomas Gomborg, who will talk about wrapping corrections for long-range spin chains. So please.
Thank you. At first, I would like to thank the opportunity to present my recent result on long-range spin chains. And the goal of this talk to show you how to define spin chain interaction when the range of the interaction is larger than the length of the spin chain. This is the contents of my talk. I start with the motivation part. After that, I show the definition of the asymptotic long-range spin chain. And after that, I show a construction for transfer matrices for this long-range chain. We will see that this transfer matrix gives a method to define finite size long-range Hamiltonians, and I finish my talk with some requirements coming from the Adscft duality. Okay. Actually, I have an easy job in the motivation part because my motivation comes from the topics of the previous two lectures. So we saw that in N equals for super Young-Mills, some quantities like defect one-point function and the three-point function of determinant operator, and also one-point function in this RP4 N equals for super Young-Mills. So these quantities are connected with an overlap between boundary state and beta states corresponds to the single trace operators. And there are lots of results for these overlaps, for example at tree level, and also some results at strong coupling, and also for finite coupling, but this finite coupling results mostly concentrated on the asymptotic region. And the most important open question, how we can calculate the wrapping corrections for these quantities. For more details, let me give a brief review for the integrability approach for calculating the two-point function of the Adscft, which is of course well-known stuff. So we have two sides. At the gauge theory side, we have long-range spin chain with length j, and the string theory side, the theory can be described by the one-dimensional sigma model with length j. And at the asymptotic limit, when the length goes to infinity, from the perturbation theory, the dilatation operator can be calculated, and the leading order is two-site interaction, next order is three-site interaction, and so on. And this dilatation operator is integrable, which means there exist higher charges, for example, this Q3, for which the bleeding order is 3-site integrable, the second order is 4-site integrable, and so on. Because of the integrability, the spectrum can be obtained from an asymptotic beta ansatz. And we have to note that this Hamiltonian for the N-equals for super Young mills is a very complicated object, because the local space, so the local Hilbert space, is infinite dimensional. And also there is a dynamical effect, which means that the Hamiltonian can change the length of the operator. For example, 2 fermion can scatter to 3 scalar. And for these reasons, it's efficient to use some toy models for develop methods and test the ideas. And so good toy models can be the long-range deformation of the GLN spin chain, for example. Okay, at the string theory side, the anomalous dimension are the string energies, and infinite lengths, the dispersion relation and the scattering matrices are known, and this defines the spectrum, and this infinite length, the spectrum can be is given by the asymptotic beta ansatz, and the toy models for this setup is the simpler 1+1 dimensional field theories. And of course, the asymptotic beta ansatz in the two descriptions are the same. And what happens at finite lengths? So for lengths which are, for the perturbation order, for which the range of the interaction is bigger than the length of the chain, the asymptotic beta ansatz cannot work anymore, and wrapping corrections appears. But there is no good spin chain description for these wrapping effects. So in other words, we haven't got any method which tells us how to define interactions in a spin chain where the length of the chain is smaller than the interaction range. And the solution for the wrapping correction comes from the field theory description. In the field theory, we know so the finite size correction appears at finite lengths, and this finite size correction agrees with the wrapping correction coming from the dilatation operator. And all the finite size correction can be handled with the thermodynamic beta ansatz, and of course there are more sophisticated techniques based on the Y, T, and Q systems. And these methods was so successful that the investigation of the long-range spin chain stopped at the asymptotic level. But for other quantities, for example, the G function, some problem appears when there are bound states in the spectrum, and excited TBA equation cannot be simply obtained by analytic continuation. So therefore, other methods are necessary to calculate such quantities. That is why I think it's worth to come back to the spin chain description and find how to define spin chain where this wrapping effect can be investigated. And I think this can be open new perspectives for calculation in the Adscft, the planar limit. Okay, let's continue with the basics of the asymptotic long-range spin chain. As I mentioned, dilatation operator can be written as a series expansion, and Hamiltonian, the interaction range of the Hamiltonian grows by order of the coupling constant. And I use this notation HL for the order L in lambda, and this HL is a Hamiltonian with interaction range L plus 2. And clearly this Hamiltonian is defined only for the lengths which are bigger than the interaction range. So this is the asymptotic region for this order of the perturbation theory. I also use some graphical notation for this Hamiltonian. So for example, this is the nearest neighbor Hamiltonian, and this is the Hamiltonian with three-side interaction. For integrable Hamiltonian, there exist higher charges, for example, Q3, and this Q3 has these interaction ranges. And we can expand this equation order by order. The leading order is the usual integrability condition for the nearest neighbor model. At the first order, we have a non-trivial condition for H1 and Q13. And the second order, we have a new constraint for H2 and Q32. Using this equation, starting from an integrable two-side spin chain, we can obtain these higher Hamiltonians order by order. And for the explicit calculation, we know that there are unfixed parameters. The first class of this unfixed parameter comes from the similarity transformation of the charges, which is obviously defines commuting charges. And this U is just the sum of local operators, and these coefficients epsilon are spectral parameter dependent unfixed parameters. And the second class comes from the fact that the linear combination of the charges also define the commuting set. We can see that this gamma has no effect on the eigenvalues, and this epsilon has no effect on the spectrum. Therefore, these are unphysical parameters. The physical parameter can be obtained, the argument of this paper. So if the derivative of the charge with respect to the coupling constant is a commutator, and for leading order these sets of charges are commuting, then it is a consequence that these charges commuting at finite coupling as well. The only consistency condition is that this commutator has to be a local quantity, and there is two choice for this X operator. It can be a boosted version of conserved charge and also a bilocal combination of conserved charges. So in this X, two new type of parameter appears. And in the next slide, we will see these are physical parameters. So let's see an example for a long-range deformation. So for the original XXX spin chain, it is well known that the spectrum can be obtained from the Bethe-Ansatz equation, where this U is the rapidity parameter, and this equation connects the momentum and the rapidity parameter, and the charges are just sums of local densities. And it turns out that long-range deformation, the Bethe-Ansatz is modified in two ways. So we have to redefine the connection between the rapidity and the momenta, and a new scattering phase appears in the equations. And it turns out that this alpha parameter defines this rapidity map, and the beta parameter defines this extra phase. And the gammas are just the linear combination of the charges, and we see that the epsilon parameter is completely disappear for the spectrum. Okay, so let's continue with the construction for the transfer matrices. This construction based on the recently introduced algebraic framework for medium range spin chains in these two papers. So we call a spin chain medium range if the interaction range is bigger than 2 but finite. So in this, so I will use this notation for the L+2 site interactions. So we can see that this Hamiltonian is a sum of densities, and this density operator acts on non-trivially on L+2 site, and also use this shorthand notation for the density with interaction range L+2. And it is clear that this Hamiltonian is also is only defined for lengths which is bigger than the interaction range L+2. And I also use a notation for this density operator. So this is a 6-site interaction example. And we define Lox operators with this regularity condition, which is, so we restrict the leading orders in the spectral parameter. So the leading order is just the identity operator, and the second order is a Hamiltonian density operator. So this Lox operator has the same interaction range than the Hamiltonian density. And this is the graphical interpretation for this regularity condition. So the spectral parameter dependent Lox operator is equal to the identity plus u times the Hamiltonian and other terms. We also introduce an R matrix which has interaction range 2L+2, and this satisfies the RLL relation. And this is the graphical interpretation for the case when the interaction range is 5. So this red box is the R matrix, and these are the Lox operators. And if we commute the R operator, so the action of this commutation is that the rapidity parameter are changes in the Lox operator. So this is the RLR relation. And we can also define transfer matrices, which is a product of shifted Lox operator. And also we introduce this shifted or twisted trace. So for interaction range 4, we introduced 3 auxiliary space. And we have to trace out this 3 auxiliary space in this twisted way. So we take the first incoming leg and sum with the j+1 outcoming leg. And we trace out the second incoming leg with the j+2 outgoing leg, and so on. So this is the definition for this twisted or twisted trace. Okay, so this is the definition of the transfer matrix. So be more familiar with this notation. Let us show some properties of the transfer matrix. So at first, let us start with the definition of the transfer matrix. We can add an extra site. So in this site, the Lox operators act trivially, and after doing the summation with this outgoing and this incoming node, we obtain just the previous diagram. But in this case, we can see that there is summation for these 4 incoming legs. Therefore, we can replace this Lox operator to that place, which is just the cyclicity property of the twisted trace. And now, this Lox operator acts trivially on this first side. So therefore, we can do the summation for this incoming and this outgoing leg. And doing this summation, we obtain this diagram. So we can see that this is the original transfer matrix, but we did a shift, a cyclic shift in the outgoing and the incoming legs as well. So with formulas, this relation tells us the transfer matrix is invariant with respect to this cyclic shift, where this U is the shift operator. Okay, let's derive another property of the transfer matrix. So if we take this diagram, where this red box is just an R matrix, and I review the RLR relation for this situation. So we can see that we can apply the RLR relation for these three operators. So we have to shift this red box with one side to the left, and also we have to change the spectral parameters in the Lux operator, and we can see that we can obtain again, well, we can use again the RLR relation. And repeating this method, we obtain this diagram. So now we can multiply the two sides of the equation with the inverse of this R matrix and take the twisted trace with this 6 auxiliary space. So now we can see that we can replace this R matrix to there using the cyclicity property of the twisted trace. So we obtain this diagram. And so this products of Lux operator is just the transfer matrix, and these products are the shifted transfer matrix. And this is true for the other side. And using the fact that the transfer matrix is invariant under the shifts, we obtained that the transfer matrix defines commuting quantities. So this is just an integrability property. Okay, so let's continue with the generalization to the long-range case. For this, I define the truncated Lux and R operators. So these calligraphic letters means that this depend on the spectra, the coupling lambda. And we define this level L Lux operator as a series expansion in the coupling constant up to order lambda to L. And we define also this level L R matrix as a series expansion in the coupling. But in the definition of this level L Lux operator, we use the previous L operators. So for level L operator, it contains the Lux operators of the previous levels for lower L's. But for the R matrix at level L, we use completely different R matrix for each level. So in the series expansion, these R operators have two indexes. The first index label the level, and the second index corresponds to the order in the coupling. So this definition needs for the consistent algebraic definition. We will see the details now. So we define the RLR relation just as for the medium range case, but now we define this in a truncated way. So we have so this equation is satisfied only for this order. So this is a L+1 equation for these orders in lambda. And now let us assume that there exists a solution of this equation. So there exists a level L Lux and R matrices, and let us take a next order. So next level equation for L+1, which looks like this. So for the first L+1 order, this equation contains only just L matrices 0 to L. Or in other words, if we neglect the highest order of this equation, we just remain only this first L+1 order. this equation looks like this. So in this order, the L plus 1 level Lux operator becomes the L order Lux operator because of this definition. And we can see that this is a completely different requirement for this level L Lux operator as the defining one. So if we go higher and higher levels, new and new requirement appears for this level L Lux operator, which is obviously not a consistent definition. But this can be consistent if it is guaranteed that these new equations appearing at the higher levels are exact consequences of the first definition for this Lux operator. And this turns out this is the case. So neglecting the highest order of this matrix, the first L plus 1 order can be obtained by the level L quantities, where we introduce the formal inverse of the Lux operator. So using this definition for the next level R matrices, this equation is a consequence of this. And we can see that this Lux operator, where the first index is bigger than the second, are fixed completely by the R operators with the coinciding in the upper indexes, which means that in this construction, the real unknowns are this LL matrices and this RLL. And the only non-trivial condition appears from this truncated error relation at the highest order, so for order lambda 2L. And this is this equation in that order, and we can systematically solve this equation, obtaining higher and higher order L and R matrices. And this is the only requirements for these expressions. Okay, so now we can define the transfer matrix, and we define it with this truncated way. So use the same definition as was for the medium range case, but truncated at order lambda 2L. And one of the consequences of the truncated error relation that this transfer matrices define commuting quantities up to order lambda L plus 1. And we also require this regularity condition for the Lux operator, which is the same as before. So the leading order in the spectral parameter is just the identity, and the second order is just the Hamiltonian density. And the Hamiltonian density can be series expand, and the interaction range of this operator agrees with the operator ranges in the definition of the asymptotic long-range Hamiltonians. So this interaction range is k plus 2 at order k. The consequences of the regularity conditions are the following. So the first one is the transfer matrix is the identity at u equals 0. And the first derivative at u equals 0 is just the Hamiltonian, which can be series expand. And for lengths which are bigger than the interaction range, these Hamiltonians are just sum of densities, and then this HL has interaction range L plus 2. And this is agrees with the definition of the asymptotic long-range Hamiltonians. So the regular solution of this truncated error relation gives integrable long-range pinch chain by Hamiltonians by definition. The only question is the reverse direction also true? In other words, are there Lux operator Frere integrable long-range pinch chains or not? Obviously, I cannot answer this question, but I investigated the long-range deformation of the GLN spin chain in the first non-trivial order, and I found these Lux operators that exist for every physical parameters of alpha and beta. So I think it's a strong observation which says that this Lux operator exists for general long-range models as well. Okay, let's now continue with the finite size long-range Hamiltonians. So the main advantage of this transfer matrix, it is well defined even when the length of the spin chain is smaller than the interaction range. So it is defined even for the wrapping region. So the Hamiltonian is just the derivative of the transfer matrix, so let us calculate this quantity. So let us see an example where the interaction range is 5 and the spin chain length is 4. Taking the derivative, we obtain a sum of 4 terms. And these terms are the derivative. So these blue boxes are the derivative of the Lux operator, which is just the Hamiltonian by Hamiltonian density by definition. And we can see that we can do this summation for these legs and also these legs and also these legs. So we obtain this sum. This first term is just the twisted trace of the Hamiltonian density. And the second term is a cyclic shift of the first one, and the third term is the double shift of the first one, and so on. So more generally, the Hamiltonian at order L is just a sum of a shifted version of this H1JL operator, and this operator is just the twisted trace of the original Hamiltonian density. And this is another example. So for example, if we have 8-site interaction and we want to calculate the corresponding operator at length 5, then we have to trace out these 3 extra leg. So this is the definition how obtain a finite size Hamiltonian from the asymptotic one, and by this definition it has also a higher amount of conserved charges because these transfer matrices are commuting by definition. Okay, let us see a physical consistency condition for this definition. So let us take any finite volume long-range spin chain for every length j. It obviously defines an asymptotic Hamiltonian by taking the limit j goes to infinity. So for this Hamiltonian, we can apply the method and we obtain a finite size Hamiltonian. And the physical consistency, this new Hamiltonian should agree with the initial ones. So it's a very natural physical consistency. So let us check our method satisfy this condition or not. And we check this statement on the Innocent-Chapter spin chain, which is a long-range, non-long-range Hamiltonian on finite length. So this is the Hamiltonian, P is the permutation operator, and this P and zeta are the Weierstrass P and zeta function on the torus with periods j and omega. And this omega is a completely imaginary number, and this kappa is a real coupling constant. Taking the asymptotic limit, we obtain the hyperbolic Innocent-Chapter spin chain, which is given by this Hamiltonian. And we can apply our method to this asymptotic Hamiltonian. So this Hamiltonian contains only just the permutation operator, so we have to use this formula for this permutation operator. So this is an example for permutation between site 1 and 8. So this red box shows that this permutation acts non-trivially only the site 1 and 8. Using the properties of the twisted trace, and then let us set j equals to 5. So we want to calculate the 5 lengths version of this 8 lengths operator. So we can see in the wrapped case this permutation acts non-trivially on the site 1 and 3. So this is just the permutation 1, 3. And this 3 is just a reminder of 8 modulo 5. And we can generalize to the general permutation, and we obtain that this P1k is just P1 mod kj. If this residue is not 1. For 1, just the identity operator. So substituting this result for our formula for the finite volume Hamiltonian, we obtain that the Hamiltonian is constant plus sum of permutation times an infinite sum. And we can do this summation, so the closed form is known for this summation, which is exactly the potential of the original Asymptotic spin chain. So we just showed that for Asymptotic spin chain, this physical consistency condition is satisfied. So it's physically meaningful definition. Okay, let us see some requirements from the Adscft duality. So my first argument comes from the fact that the anomalous dimension of the single trace operator is equal to energy level of 1 plus 1 dimensional field theory. And we know in the field theory description the asymptotic data, which is the dispersion relation and the scattering matrix, defines uniquely the finite volume spectrum. And it is not natural assumption that in the spin chain description, the statement is also true. Therefore, the asymptotic Hamiltonian is completely defined and uniquely define the finite size Hamiltonian. And we saw that the method I showed you provides unique finite size Hamiltonians. So it's in agreement with this mapping between spin chain and field theories. And my first argument comes from the fact that in perturbation theory of dilatation operator, unfixed parameter coming from the free choice of the renormalization scheme, and because it's just coming from the renormalization scheme, they cannot appear on physical quantities. Therefore, these are unphysical parameters which disappear from the spectrum. Therefore, these parameters coming from the renormalization scheme corresponds to the epsilon parameters of the asymptotic long-range Hamiltonians. But in the perturbation theory, we obtain Hamiltonian even in the wrapping region, and this parameter is still there, but the parameter is still non-physical. Therefore, this epsilon parameter should have to appear also from the finite size spectrum. And this is a non-trivial condition for a method which gives us finite size Hamiltonians. So to be more concrete, the epsilon parameters coming from the similarity transformation of an original asymptotic Hamiltonian H. And it can be proved that if we apply our method to obtain the finite volume version of this H tilde, so the rotated one, is just given by a similarity transformation of the original finite size Hamiltonian. So this Hj is the finite size version of H, and this H tilde j is just the finite size version of H tilde. So these epsilon parameters are in this uj, which is the finite size version of this original local operator. So from this argument, we can see that our method gives a finite size Hamiltonian, which the spectrum is independent from the epsilon parameters. Okay. So the second argument. So now let us consider asymptotic Hamiltonians for the n equals 4 super Young mills, one of the long-range deformed SUN and SU2 spin chains, for which the SU2 subsector are the same. So choosing these Hamiltonians, let us assume the finite size version of these Hamiltonians. In the Adscft, the wrapping correction of the SU2 sector includes contribution for the full spectrum. This is clear from the Blucher picture, where we have to sum all the excitation, not just the SU2 excitation, and also from the quantum spectral curve, where we also have to solve the full Q system, not just the Q functions of the SU2 sector. So for the Adscft, we obtain that at finite size, the restriction to the SU2 sector is not equal to the SU2 Hamiltonian at finite size, because this contains contribution for the other sectors. Let us see our definition for the wrapping region. So for the wrapping region, we have summation for these ingoing and outgoing legs. And of course, this summation belongs to the full representation of a one-side state. So the definition of these operators contains information of the full theory. So for our definition, if we calculate the wrapped, so the finite size version of a SUN spin chain and restrict to the SU2 sector, this Hamiltonian contains information from the full theory. Therefore, it cannot be equal to the finite size Hamiltonian of the SU2 model. So this is in agreement with the property of the Adscft. Okay, my last argument. So the for-loop asymptotic dilatation operator in the SU2 sector contains transcendental number zeta 3. But for length 4, which is already the wrapping region, the dilatation operator in the SU2 sector contains not just this zeta 3, but zeta 5 as well, which means that the finite volume Hamiltonian could contain extra transcendental numbers. Let us see our definition. So in this setup, so this is the 5 interaction range 5, which corresponds to the for loop, and we apply our method with spin chain length 4. So this contains a summation with this outgoing and incoming legs. And for infinite dimensional local Hilbert spaces, we have an infinite sum, which may result extra transcendental numbers. And so this is the case for the n equals 4 supernomials as well. So this definition, which contains this summation, can be in agreement with the properties of the SU2. N equals 4 super Young means, so extra transcendental can be appears. Okay, so these are my conclusions. So the main message of this talk is if we have a spin chain interaction, then we can obtain the finite size version of this interaction using this twisted trace diagram. And more specifically, I showed the perturbative construction for transfer matrices, which gives the long-range Hamiltonians and higher charges. And I checked that this construction gives all the long-range deformation of the SUN spin chain up to this order. And this transfer matrix can be used to define Hamiltonian with finite lengths, and we saw that this finite Bolton Hamiltonian satisfies some properties of the Adscft wrapping corrections. The first one was that the finite volume spectrum is independent from the parameters epsilons. The second one was the wrapping correction of closed sectors depends on the full spectrum, and extra transcendental number can appear in the wrapping corrections. Thank you for your attention.
Thank you very much for this interesting talk. Do we have some questions? Florian?
Yeah, thanks for the nice talk. So if you have these GLN spin chains that you mentioned with these parameters alpha, beta, can you explicitly complete them to exactly integrable spin chains with this formalism? I mean, they are asymptotically integrable, right? Before.
Sorry, can you repeat?
These GLN spin chains that you mentioned, they are asymptotically integrable with these parameters alpha, beta. Can you complete them to exactly integrable finite size spin chains?
Yeah. So I can construct the explicit finite size version up to some order. So I calculated the Lux operator up to lambda to square. So I can construct the finite version only this lambda square. So I can obtain the higher charges as well for up to lambda square.
Okay, so you do it order by order, but in principle...
Yeah, so at this point I can calculate the Lux operators order by order at this point, but maybe in the future we have a better computation for the Lux.
And can you also get the monodromy, the deformed monodromy, or only the transfer matrix?
Yeah, so I have the transfer matrix, and these are commuting even at this finite length. So.
I mean, the transfer matrix is the trace of the monodromy, right?
Yeah.
So if you get the monodromy, you would also get, say, the deformed Yangian symmetry, how the Yangian acts on finite size spin chains.
Yeah, but in this case, the auxiliary spaces can be very high, because so the monodromy matrix so for interaction range 4, so this is the third or second non-trivial order. So we have tensor product of 3 sides of auxiliary space in the monodromy matrix. And if you go a higher and higher loop, then you obtain higher and higher dimensional subspace. And at this point, I didn't analyze this higher space of auxiliary space.
Okay, thank you.
Okay, Didina also had a question. Didina, just besides.
Yeah, thank you for this nice and endearing talk. So my question was somehow related to the one of Florian. So can you give more details about the construction of the R matrix that you are using to prove that this monodromy matrix is satisfy Yang-Baxter? So yeah, the R1L.
So can you repeat the question?
How these R matrices RL are explicitly built?
So,
for example, R on this formula on the screen, R1L0. What it is explicitly?
So
Yeah,
the explicit form in R00 is just the usual nearest neighbor R matrix, and for higher order, I calculated the explicit form up to L equals 2, but these are very, very complicated, and in my paper I only put the first order, this R1, because the R2 is just, I don't know, it can be written only for 2 pages. Or
yeah, that would be nice to, yeah, to
maybe it can be written in a more compact form, but I didn't try to make it a compact form.
Okay, thank you.
Okay, more questions? Okay, seems not. So let's thank Thomas once more for his.
Yeah, so let's leave for the lunch in 10 minutes in front of the building. Everybody is welcome.
only.
The stream. So welcome back to the afternoon session of IGST 2022. My name is Matthias Staudacher from Humboldt University Berlin. I'll be chairing this the next 3 talks. For the first talk, I actually have a slight conflict of interest, as you will see in a second. So that means that you're only allowed to ask nice questions after this talk. Anyway, so we have Changrim An from Eva Women's University in Seoul, who will be talking about some connection between so-called Polya formula and Jordan blocks in spin chains.
Thank you. Of course, first of all, I want to thank organizers for kind invitation. So as I introduced, I'll talk about Jordan block, which is quite rather conflicting with the integrability. And what I'm going to say today is basically that standard integrability technique sometimes are not enough to solve the integral models. This talk is based on 3 papers as a result of a wonderful collaboration with Matthias, of course, in our chair, and Luke Corcoran. I'm not sure whether he's around. In the first work, we basically found that certain integrable spin chain model has a very rich Jordan block spectrum, which can be only discovered by some kind of phenomenological way. And we applied, which I'm going to explain, the standard technique of integrability to explain those, but failed. And in our second work, which is the main part of this talk, is that we changed our strategy from using integrability to using some kind of a mathematical technique like combinatorics or linear algebra, etc., to find out the so-called Jordan, this rich Jordan block spectrum, which we succeeded. And in third work, we improved some case which is quite generic, which you will see that some generic number of the field contents into certain very beautiful formula based on Polya. Why it is in the name? His name appears in the title. Okay, the story begins in the so-called fishnet model, where many of you, several talks already has been given today or yesterday, where all these authors introduced this, the coupling constant goes to general limit, while these 3 deformation parameter goes to imaginary infinite, such that certain combination can be finite. There are several different choices, but I'm going to focus on some the cases where Q's goes to infinite, such that G goes to general limit times this infinite has a finite value. Then this fishnet model, or generalized fishnet model, where fishnet model is usually including only 1 parameter, and generalized fishnet model has 3 these parameters, has this kind of Lagrangian. And shortly after, these authors, including Matthias here, studied the spectral problem of this super-Yang-Mills, kind of super-Yang-Mills theory. And since G goes to general limit, 1 loop is usually enough. And the dilatation operator is described by certain specific spin chain model, which they named eclectic. I don't know why, personally, but anyway, that's the name I adopt. And it is just given by some kind of a chiral permutation operator. So since we are considering this 3 scalar sector of the super-Yang-Mills theory, I'm just trying to say for short notation that instead of this pi 1, pi 2, pi 3, I'll just denote the number 1, 2, 3. And then since we are dealing with the single trace operator, which should be cyclic, so we should consider certain combination of 1, 2, 3s in cyclic form. Okay, when I say cyclic, well, sometimes I'm going to omit it. It's basically summation of all possible the cyclic rotations. And this chiral permutation operator is acting on certain special case where, say, this P21 acts only when it sees 2 and 1 together, and it changes 2 with 1. When it acts on 1, 2, it just kills it. That's why difference from the usual permutation operator. P13 and P32 is similar. And this seems a very simple spin chain model, which is, of course, non-Hermitian, though. It's integrable because it can be constructed from the so-called R matrix, 9 by 9 R matrix, which satisfies Yang-Baxter equation. And one can construct the monodromy matrix and transfer matrix, etc. And thanks to the Yang-Baxter equation, this transfer matrix commutes. And there will be infinite number of conserved charges. One of them, most important, is Hamiltonian, which is the logarithmic derivative of transfer matrix with U to be 0. Or the more simple case is just a set U to be 0, which is actually nothing but shift operator. Yeah, so P1, 2, 1, X1, 1, 2 is 0. It's simply 0, it kills it. So if instead of 2, 1, if this operator acting on 1, 2 state, it's 0. So, well, one can try first of all this standard, say, algebraic Béransat, since it's integrable. So, since we already constructed the monodromy matrix, one can try to apply this commutation relation, so-called fundamental commutation relation, to find the eigenvectors. But for example, if you write down this commutation relation for some simple cases, actually it looks like this. So here the R component is just 1 from the R matrix. So basically he said that this diagonal component of monodromy matrix times some creation operator is just again the same order. So it's not commutation relation. To find the commutation relation, actually you need some this operator to commute whatever the arguments are. But here there's no commutation relation. So integrability already fails. So we relied on the MATLAB or Mathematica or some numerical calculation, and then we found that some quite interesting spectrum, Jordan block spectrum, which I'm going to show you soon. So in these circumstances, the eventual goal of integrability, which is some special form of the integral model like a spin chain, is to diagonalize Hamiltonian, basically, right? Which is quite large size and a systematic way of finding eigenvalues and eigenvectors. But that goal is already from the beginning cannot be realized because Jordan block never can be diagonalized. The best thing you can do is to transform this Hamiltonian into the most closest form of diagonal matrix, which is Jordan normal form. So what are they? Just to review some of that, let's consider certain matrix H, which is a highly degenerate. So that actually, to simplify the situation, let's consider that all eigenvalues are same. But there are many different eigenvectors. So this psi 1j is eigenvector of Hamiltonian with the eigenvalue E. And there can be many. So let's consider them to be gamma. And sometimes this is called, in mathematical literature, geometric multiplicities. Then for each eigenvector, for satisfying this first eigenvector relation, then one can find associated generalized eigenvector where they vanish only when you apply some number of these H minus E operators. And of course, this M can be increased as many as possible. So total number of this kind of generalized eigenvector and eigenvector is sometimes called algebraic multiplicity, which I'm not going to use. Then one can find Jordan block that starting from some highest vector, we will call top vector, and acting this H minus E successively, then it will reach it to psi 1, which is eigenvector, because if you act H minus E one more time, it's 0. So this is forming Jordan chain, and this Jordan chain converted into matrix form is nothing but just Jordan normal form. Okay? Where all the diagonal element is eigenvalue same as E, but we need one more off-diagonal element, which is normalized to be 1. Then what happens in our eclectic model? Actually, if we numerically study this Hamiltonian of eclectic model, then we found that there are certain numbers of Jordan blocks appear with a certain number of multiplicities. Say from N1 to the size capital N1 Jordan block appears small N1 times, and so on. And then for short notation, we'll write down this spectrum as this capital N1 to the N1, capital N2 to the N2, etc., in the some ordering way. And since this pi 1, pi 2, pi 3, using this the fishnet Lagrangian, numbers are preserved, is a good quantum number. So sometimes we'll say LMK sector, where actually this is a Bethe-Ansatz terminology, that L is total size of spin chain, M is the number of Bethe roots in the first level, and K is number of Bethe roots in the nested level. But from just considering 1 to 3s, this L1, which is L minus M, is number of ones in the operator, or pi 1, and M1 is M minus K is number of pi 2, and K is number of pi 3s. They are all preserved. And since, we can already redefine this pi 1, pi 2, pi 3 with another pi 2, pi 3, pi 1, whatever, we'll introduce this condition, we will call filling condition. The number of ones is always the largest, and number of twos are second largest, etc. Okay? Otherwise, we can change the definition. And also, we can consider this fishnet version of the model, spin chain model, which we call the hyper-eclectic model, that this two-parameter cushion to be 0, and only psi 3 is non-zero, which we can normalize to 1. And so this hyper-eclectic spin chain is just considering P, including only P2-1 permutation operators. And it's very interesting that actually we found that this hypereclectic model and eclectic model have exactly same Jordan block spectrums, which I'm going to discuss more later. So using this hypereclectic model, we generated this spectrum for example, this m equal 5 and the k equal 1 with a various number of L. And somehow this L equal 18 is some kind of the limit of my desktop computer. And it shows the very strange number of the size of Jordan blocks and the multiplicities. And similarly, some increase, actually in this case decreasing, we consider m equal 4 and k equal 1, and we found also similar sets of the Jordan block spectrum. And one can see there's some kind of a thumb rule that how kind of size appears and how kind of multiplicity appears, but it gets really complicated as L increases. So some kind of regularity certainly exists, but we cannot find it. And also here, our numerical calculation is based on k equal 1. But if we increase k to higher, actually we could not do it even numerically. So how to understand this problem? So we'll start with integrability first. As I said, from the beginning, algebra balance did not work, I said. But still, we can use it because we can start with some finite value of q's. And this spin chain is integrable with a finite q. And then after getting this equation, we'll take the limit where q goes to infinite. So this is the result of this finite q case. And the first equation is eigenvalue of transfer matrix. And the second and third equation is the Bethe-Ansatz equation. And the last line is the Bethe vectors in terms of the algebra variance. So using this equation, we'll take now the singular limit where q goes to infinite. So we introduce this parameter epsilon and the psi, and replace it into the Bethe-Ansatz equation. And then the equation themselves have a certain factor of epsilon, and which epsilon goes to 0. And this, because of this extra singular factor, we found that the solution of this Bethe-Ansatz equation can be solved analytically, and they are all collapsing into certain same value. For example, this u, which is the first level Bethe root, there are two kinds, the associated with just up to m1 or associated with the second level Bethe root. So this first one is from 1 to m1, and then on a second kind of first Bethe root is a k number of them. And this exponent and also this coefficient can be found explicitly here in terms of LMK. And then this finite part of coefficient of this epsilon term can be also obtained, where you can see that this coefficient is given by, for example, in terms of this integer nk, and the second Bethe roots are given in terms of the integer in. So since, if you have Bethe-Ansatz equation, there are many kinds of different sets of Bethe-Ansatz solutions. So each solution is just given by choosing this integer sets from nk set or in sets. So for example, if there are the m1 number of uns, then one should choose the n different number of this integer from 1 to L, and that defines one set of the Bethe-Ansatz solutions. Well, unfortunately, this scaling ansatz is valid when alpha and beta is positive, but certainly to satisfy beta to be positive, this L should be less than 3m1. So actually, L should be bigger than 3m1. So when L is less than 3m1, this scaling ansatz is not valid. We don't find the solution in that case, unfortunately. But actually, usually the chain size, which is L, is usually much bigger than number of Bethe roots. So actually, those small window is not really the losing interesting cases. So using that, we inserting this back into the transfer matrix eigenvalue. Then we found, first of all, that all the size disappears, completely canceled out. And then, as I said, since we are going to take this limit where not only Q goes to infinite, but also we should rescale this U to epsilon times U bar. So from the eigenvalue equation here, one can notice that since U goes to 0 here, because it's a factor of epsilon, so this eigenvalue is the same as when U equals 0. So in this case, eigenvalue of the trans matrix is actually same as eigenvalue of T of 0, which is shift operator. So when you shift L times of this spin chain, you go back to the same chain. So all the eigenvalue of the transform matrix should be Lth root of unity, which you can see from here, that this exponential factor, and they are all integers. So this is just root of unity. So this psi independence already shows some kind of universality. And also, we are interested in, as I said, single trace operator. So we'll consider cyclic state only. And this can be obtained when the square bracket is 0 mod L. So one can choose all possible beta roots, which can give the square factor to be 0 mod L, which you can count from using some mathematical program, which is very easy to do. On the other hand, this famous Hungarian-born American mathematician George Polya's formula is entering. Although he said something very humble, this beautiful mathematics will certainly help a lot in theoretical physics. And according to him, basically his so-called enumerator theorem has a much wider applicability. But just to our problem, we'll just simplify the theorem that we want to count all different sets of the necklaces made of L number of beads, and each bead has a certain number of colors. Here we have 3 colors, 1, 2, 3. How many different kind of necklace can you make? And the best formula derivation I know of is actually done by Spradlin and Bolovich, who are physicists, when they want to compute the partition function of super Yang-Mills theory, is that we consider this generating function here, G, where this is trace of all tensor product of these 3 different colors. That means a bead. And the L bead consists the necklace. And this operator L is a counting number of 1 beads in the necklace, and M is a counting number of these blue beads, and the K is counting number of 3 beads. I mean the red bead. But since we should consider only cyclic state, we should include also this projector, cyclic projector, which is the given by this U, which is a shift operator to the power J. And this formula is very useful. For example, let's consider that this trace means that it's a sandwiched with this A1, AL state in both sides. But when, for example, J equal 1, so U is acting on this first state, then it will shift each side. So instead of A1, A2 to AL, it becomes A2, A3 up to A1. And since this state is acting diagonally on these LMK operators, we need to compute this kind of inner product. So the first one is the A1 should be A2, otherwise 0. Second one said A2 should be A3, etc. So actually, this dictates that all the colors should be same. Actually, this is true when J is co-prime to L. And if J and L is not co-prime, for example, if the greatest common divisor of J and L is 2, then you can notice that this color should be same every even side, and independently every odd side it should be same. So number of ones is easy, that just 1 times, for example, in J equal 1 case is L, because there are L number of 1 state. If its state is 2, then it should be 1 times L, because again, number of 2s should be L, because they are all same colors. When J and L is 2, there are two different identifications. So total number 1 is L over 2. And the odd side is also L over 2. So it should be just a trace of the square. So one can continue this into J and L to all other numbers. And one can easily write down this generated function into this form. And then one can count also how many different number of integers which have the greatest common divisor with the J and L to be P, which is actually easily understand because if you divide both sides by P, then J comma L over P should be 1. That means that they should be coprime. So there is some function which counts the number of coprimes of n, which is less than n, which is a so-called Euler-Tauschant function. So in terms of Euler-Tauschant function, one can write down this generated function into this form, which also can be also summed up partially, such that it can be written in terms of this law. Where this partition function zeta is applying for just single bid state, so it's a trace over x, y, z. So it is just a simple x plus y plus g. So in this xn, yn, jn, it's just replacing xn, yg with xn, yn, zn. So we obtained this generating function. And then if we expand this in terms of number of the x's, I mean ones and number of twos and number of threes, then the coefficient, which we call d, is counting number of cyclic states in LMK sector. So we have two different ways of solving the problem. And this is the result. So the first column is just we call the naive counting because just the number of partitions divided by L, because we just naively thinking that a single rotation is giving same the necklace, so just divided by L blindly. So of course this is observed. But second column and third column matches exactly that the Bethe-Ansatz result and the Polya formula is indeed correct. So this confirms that this Bethe-Ansatz equation and this solution is correct, but still, where is Jordan block size? This just counts the so-called algebraic multiplicity, just total size. It does not give any Jordan block spectrum. Also, since we found the Bethe roots, one can use this algebraic balance to insert into the creation operators, and can try to see whether there is some eigenvectors. And the result is that actually what we can find is only one vector. So all the eigenvectors of this finitely twisted model is all collapsing together into one vector, which is locked state, which has some very ordered form of these excitations. So first the M1 number of twos appears, and then the K number of threes appears all in a row. And this very disappointing result, because since I showed that every Jordan block should have eigenvector, and I showed a lot of eigenvectors. But unfortunately, this algebraic balance gives only one eigenvector. And the same conclusion has been obtained by some independent work on these authors using coordinate Bethe-Ansatz. And online question. Yeah. Multi-trace. Yeah, I think, yeah, that's good. Yeah, one can. Because of this, yeah, actually, I'm going to explain related problem, and maybe he can ask again. But the main difference here is that Polya formula appears only when the single trace over is cyclic, right? Multi-trace is not cyclic? Yeah, maybe. Yeah, anyway, it's not planar limits, right? So, okay, so the real question is that all this integrability cannot give the eigenvectors except this trivial one. Although these authors, by the way, found that the generalized eigenvectors, which is associated with this the locked state, which we can find from the Bethe-Ansatz equation, but they also succeeded to construct the related generalized eigenvector. But real question is the true eigenvectors, because they define the Jordan blocks. So, this leads me to consider this another way of approaching. So first, let's consider some cake 1 case, which is only 1 3 state, and then there are bunches of 2 state and 1 state. Then let's consider some typical configuration composed of this number of 2's, which is M1, and then there are bunches of 1's, which is L1. Then let's consider the first the 2 state, there is N1 number of 1's, and the second and third is N2 number of 1's, and so on. Then we'll define some very important quantity, which is a level, we call, is that number of these 1's on each 2 on the right hand side of each 2. So for example, the first 2, there are N1 of them, and then N2 of them, and until M1 of them. So the first number for first 2 state has the N1 plus dot 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 and N1 state. And second 2 will have starting from N2. And then the last one is only M1. And all this sum of this N1 plus N2 plus, even including N0, is L1. And then it's easy to notice that when I apply H3, they are always moving each 2 into 1 step on the right. So this level is always decreasing by 1 unit. And then the maximum number of the state which has a maximum value of the S is the case where all 2's are on the left and as far as possible from 3's, which has this L1 times M1. And the smallest value of S is given by this locked state, which is eigenstate, which we found from the Bethe-Ansatz state, which has a value of 0, because there is nothing, no 1's on the right-hand side of 2's. So it's easy to notice that even from in this configuration, that this anti-locked state is the top vector, and applying all these H's, it goes to until the locked state. And the size of this Jordan block is L1 times M1 plus 1. So this is actually explaining the largest Jordan blocks of this table. But the question is, all this, there are many the Jordan blocks in interior. How to explain that? So to understand this, let's go to some special simple case, which is a 731 sector, which has the maximum value of S to be 8. So starting from this anti-locked state, we act H in arriving this, which already I showed. But you can notice that at the level 6, there are 2 vectors. That means that I can construct some linearly independent state, which I call here A times this state plus B times this state, which can be linearly independent from the 6th state over there, S equals 6th state, such that if we act H, then it will end up to this level 1 with a certain coefficient. And if we demand that the coefficient is 0, then we can find one independent Jordan block, Jordan chains. So imposing this condition, then this one is top vector, and the other one is true eigenvectors. Then one can notice also that level 4, there are 3 vectors. That means that we can consider one more vector, which is linearly independent. So let's call the coefficient to be A prime, B prime, C prime, and acting on H, then we'll have that state. But if we choose this value, then that is 0. In other words, the first vector is eigenvector. So one can notice that if we start the level S, then we can find eigenvector at level S bar, which is S max minus S. And then in that case, the Jordan chain size is this 2S minus S max plus 1, which explains why this 731 has a Jordan spectrum 159. So from this consideration, let's generalize it. So in K1, actually the most important quantity is number of this dimension of this vector space with the level S. And if they have a dimension is getting bigger than previous one, then we can find the one Jordan chain. So for example, I summarize this table, the 731, and then dimension S was this, which is number of linear independent vectors. So whenever it jumps one unit, we can find the eigenvectors and associate the size of Jordan chains. So the question is that how many kind of independent vectors one can have, which is very well defined mathematical problem, is that actually this dimension S is nothing but number of partitions of integer S into at most M1 parts, and each part cannot be bigger than L1. And it is well known that under the name of Gaussian binomial coefficients, which generate this number. So this Q binomial coefficient, which can be written in terms of product of the ratio of the Q numbers, then if we expand this in terms of Q's, then coefficient defines this dimension S. And one can easily show that this dimension of S bar, which appears where bottom vector, which is eigenvector, is actually same as the S. Then we can define the generating function, which is this trace over this Q to the S minus S max over 2. And then if we have the one Jordan chain, which starts from S to S bar, then inserting into this formula, they contribute just the Q number, which is the length of the Jordan blocks. So this generating function, which is the product of ratio of the Q numbers, if we rewrite down this formula into the linear sum of the nj Q number times small nj, then that is exactly the Jordan spectrum. Okay? So it's all encoded into this Q binomials. Then the question is how to generalize this to k larger than 1. So in this case, we need basically this Q the factor. So we define now that not only this number of ones or number of twos, etc. We define this S value, and we insert it into a trace formula, and we define this partition function as a beam. Then we are considering that this kind of a spin chain state as a kind of a necklace where k number of beads, and each bead is not just 1 to 3, but all kind of combinations of 1 to 3s, where only including one 3 state. So this color is not anymore 3, but infinite number of colors, and each color has this kind of all different ways. And since they have 1 and 2 configurations, they will all have different value of S. So we define this partition function, not only number of 1, 2, 3, but also these S values. And it's very easy, since we already computed for a given L and M, we already computed number of S's, which is generated by this Q binomial. This beam function can be easily write down in terms of this form, where this G is basically this function. So only difference from the first Fourier formula is that instead of these 3 colors, actually we have infinite number of colors. But otherwise it's all same. So we can use exact derivation as before, this formula. Instead of this L bead, we have this K bead. And each bead has not only 1, 2, 3 color, but all kinds of possible colors with 1, 3 state. Then the result should be same. So the partition function, generating function, is given in terms of this Euler torsion function. With instead of the zeta, we should use this bin function. Then we expand this partition, generating function into this number of 1 state and number of 2 state, number 3 state, arbitrary number of LMK. Then the coefficient is defining this generating function of the Jordan blocks. So it is quite straightforward to obtain the Jordan spectrum for any LMK by just expanding this master formula. For example, it only takes a few seconds to consider, say, A42, and then it can be expanded in this form, and that is a Jordan spectrum. And 963 is a different form, of course. Okay, so since I said that this hypereclectic and eclectic model have the same Jordan block spectrum, one should understand why. And let's consider that the eclectic Hamiltonian, which is composed of these three different kinds of permutation operator. And then one can notice that this level S is also playing important role here, that H3 is just decreased by 1 unit, but H2 decreased by M1 unit. M1 is number of 2 state, or H1 is actually decreasing S value by L1 unit. So already one can notice that if the S bar, where eigenvector appears, is smaller than M1, then acting H2, H1, it just kills it. So naturally, eigenvector of the hypereclectic model is the eigenvector of the eclectic model. So it's very simple. So the question is, what happens if S1, S bar is not smaller than M1? We have some kind of abstract formalism, but just to see what's going on clearly, let's consider some examples, 731 again. And then we already showed that there is eigenvector, which is given by this -9 times this plus 5 times that vector, which has been killed by acting H3 5 times. So what happens if we act the H 5 times? Then we notice that we just add certain sub-leading vectors with a low value of S, and then just find the coefficient. And if the coefficient is a 3 psi 2, then that's it. So this proves that we can, if we find the eigenvector of the hypereclectic models, then one can always find the eigenvector of the eclectic models by adding certain sub-leading terms. And they don't change any Jordan block structure. That's a kind of conceptual proof of the universality. Of course, we cannot do it all case by case because M1 and M1 is integers, and there are all different kind of property. Then it's very difficult to do it in general way. But that is just the physics proof. Okay, so this leads me to the summary and some future directions. So we basically claim that this eclectic or hypereclectic spin chain model, which has been constructed from R matrix, which satisfies Yang-Baxter equation, we cannot solve it using beta ansatz because they develop Jordan blocks. So the integral model is unsolvable by integrability technique. Instead, we need to use some kind of mathematics to find it. And we show that two applications of Jordan formula to solve possible beta ansatz equation and to find the generally k larger than 1 spin chains. And well, there will be many applications, I guess, because already I heard that several different talks on correlation functions of the fishnet model here. And since they developed Jordan blocks, it is not anymore usual conformal field theory. It should be logarithmic conformal field theory. And the correlation function should have certain logarithmic dependence. I don't know what's the meaning of it to the correlation function here, the authors are considering, but certainly they should exist. And of course, we have a kind of assumptions which I have not really addressed, but well, its mathematical proof will be quite interesting, such as, for example, universality conjecture. And also, one can try to apply our Fourier formula to other kind of non-Hermitian spin chain, which can develop Jordan blocks. Also, eventually, the Bethe ansatz is not only providing eigenvalues, but also it wants to give the eigenvectors. Here we showed how to find the Jordan block spectrum, but each Jordan block should have eigenvector, but it's not clear what is the eigenvector is. For example, let's consider this 10, 5, 1, and it has this rather simple Jordan block Jordan spectrum. But its eigenvector is much more complicated. For example, the coefficient is some special integers. And the question is is there any algebraic way to find this eigenvector systematically, which is still we don't understand completely. Okay, so I think this is what I want to talk. Thank you very much.
Questions?
Thank you very much for the nice talk. Do you think there might be a hidden symmetry behind this structure of Jordan blocks, or like
hidden symmetry?
Yeah, because there are examples of Hamiltonian with this kind of Jordan block spectrum, and there is some I don't know, GL11 for the case of UQ of SL2 at Q root of unity, or
that's
that's
a good question, which I have not thought much. But actually, I already explained that it's a highly degenerate spin chain, right? All eigenvalues are all same. That means already there are huge amount of symmetries.
Yeah, I see. We are seeing some spin chain with Jordan blocks of size. So if you have length 2L of the spin chain, we get Jordan blocks of size L plus 1, but yours are much bigger than that, I think. So in our model, we suspect there is some hidden symmetry
I see. That
underlying.
When L is quite large, you mean? As L increases, what's the scaling of the...
Yeah. It's linear. For you, is it linear or it's polynomial with higher...
Good. Yes. Actually, we have not thought about that. Also, but of course, this everything is in terms of Q numbers. That means that there should be some kind of hidden quantum group symmetry. Which we cannot figure out exactly, but certainly there should exist.
So your Q numbers are Q is what in your case?
Q is just arbitrary kind of what do you say? Like XYZ. You can just introduce certain fugacity into the partition function. So there is no physical meaning itself, but this Q is different from other XYZ in the sense that it appeared in terms of the Q number. So I mean, some kind of quantum group symmetry may exist.
Yeah. So also, I was thinking about Fabricius-McCoy, the symmetry, the hidden symmetry of Fabricius-McCoy, which appears in the XXZ at Q root of unity. There is some loop algebra behind the spectrum, and I think the usual Bethe ansatz fails for that case.
But this Q is actually different in our case because our model is rational from the beginning. There is no Hamiltonian doesn't include any.
But sometimes there are miracles. Some Q deformed model becomes some isotropic model when Q is root of unity. So I don't know. Okay.
Anyway, thank you for your question.
There's a question here, maybe.
So just first few remarks. So when we computed spectrum of super-young Mills, so we of course have to use Pauli formula. And we, of course, checked consistency of Bethe-ansatz equation with zero momentum, like for ridiculously many things explicitly. This was part of the job, of course, and we solved SUN for n, it was, but it was like part of, not even sanity. We just had to claim full spectrum. So we actually honestly did the job for, and my methods include not only PC224, but because of some dualities, actually go to SU 14 or something on the way. So yes, it's a common, but it was not non-twisted system. Yours is twisted, so it's not like honestly the same system, but of course it's very related. So the second point is about this diagonalization using counting using beta equations. So it's, I mean, we know by now that beta equations, I mean, beta ansatz is complete if you interpret properly. And this actually means that whenever you have Jordan blocks, which correspond to generalization not only of Hamiltonian, but of all conserved charges simultaneously. No, you cannot just diagonalize it with Jordan and Jordanize. So if you care about all conserved charges simultaneously, that it's impossible to have two Jordan blocks with the same eigenvalue. This is immediate consequence.
Jordan blocks with what?
With the same eigenvalue.
Same eigenvalue.
So if you care about all conserved charges, not only Hamiltonian, that's a theorem, mathematically rigorous, that not for twisted limit, but before you take the limit. But that's what you did. You first computed and then took the limit.
Yeah.
So if you care about all conserved charges simultaneously, this is a theorem that it's impossible to have two eigenvectors which share the same common eigenvalue for all conserved charges. It's impossible. It's equivalent to completeness. I mean, this is the same thing actually. It's yeah. So, but I mean.
But our case is a singular case.
No. You consider a regular case and then you take singular limit, right? So you have the generation in the spectrum of Jordan blocks because you consider only one conserved charges, which is Hamiltonian. So my first question is, why is this Hamiltonian? I mean, integrable model is the point of that we have collection. So, I mean, what distinguishes this one to consider?
It's physically interesting. I mean, the notation operator at one root.
But something else? Not yet. Yeah.
Do you want to comment on the higher charges? I mean,
on this model.
I mean, yeah, they are not the same.
Yeah, it's not because actually it's a quite singular transform matrix. R matrix itself is quite singular, so the construction of charge is not as rather different if you mod expand of this transform matrix.
I mean, you're right that you cannot find like you can if you bring like Hamiltonian in Jordan form, then in this basis the other ones are not in Jordan form. That's what you meant, right? And in fact, if you take transform matrix, you can also bring it in Jordan form, but then as opposed to diagonalizable case, basically the similarity transform will involve the spectral parameter.
And if it's a transform,
yeah.
Single,
yeah, but basically, anyway, the statement of, there's a statement theorem of simultaneous diagonalization of higher charges in diagonalizable case, but you cannot simultaneously bring all the charges Q into a simultaneous Jordan form. Well, it's not so, of course, it's actually a little bit non-trivial, but anyway, yeah, we focused on Hamiltonian because of dilatation operator interpretation.
So, as far as I understood, this eclectic chain is sort of a first-order perturbation theory of
that's right.
of fishnet. Then my question is, can you really construct states? You said that there was difficult to construct the states, but in our old paper with Korchemsky, Gromov, Sizov, Negro, we went to the second order to see the logarithmic behavior.
Second order in G?
Hmm?
Second order in
yeah, to second order.
In lambda.
First order was not enough, but second order was enough enough to construct the states and to construct then the correlator which has this logarithmic behavior, etc. So is it hidden somewhere here in your formalism, this kind of, can you demonstrate the logarithmic behavior of underlying conformal?
Yeah, I mean, if you have a Jordan block, then you should have the logarithmic correlation function.
So strangely enough, we needed really second order to see.
Yeah. So okay. So what happened in first order?
Sort of, I forgot a little bit the details. I'm looking at it, but it's You try to build the renormalization of the full set of operators.
But in the
semantic equation.
I'm not familiar with this Fishnet limit, but in the lambda square order, but still the Lagrangian contains the leading orders of Q's, right? The deformation parameter. How do you define this? The double scale limit?
Yes. And then at least you can construct all the states and construct the renormalization of operators, count semantic memory.
So it appears only from the second order.
Yeah, you needed it. Otherwise, it's not closed. The equations are not closed. So I wonder whether...
So I don't know whether Jordan block structure should appear there. I'm sure that they will in the second order too, but certainly in the first order there is Jordan blocks. And the question is why they don't contribute to logarithmic form of the correlation function. That's it depends on, of course, operator, which operator you are considering correlation function. So we are considering this SU3 sector, right? Pi 1, pi 2, pi 3 only.
It was just 5-state spin chain, and we considered all possible graphs of which renormalized the spins, but you can't avoid the second order if you do this computation.
Maybe we can discuss later.
Okay.
Also, it's different sector. It's not pi 1, pi 2, pi 3 sectors?
I mean, the point is that this is not exactly fishnet. I mean, in fishnet, you always say that the other fields decouple. So the phi 3 field decouples. But of course, if it decouples in the sense of interaction, but if you keep it inside the trace, it doesn't decouple. And that's the beauty here. You put these walls into the fishnet. It's like fishnet plus walls. And that sense is a slightly different problem. Anyway, Kolya also had a question.
So, but if you forget about phi 3, so there is still a question with phi 1, phi 2 only, that it seems some of the states they remain having 0 anomalous dimension to all orders, and some states they get dynamical. So can you say anything about counting of those states which are protected at finite lambda?
So operator containing only pi 1 and pi 2?
Yeah, only phi 1, phi 2. Can you do counting at finite coupling of states which are protected?
That case is diagonalizable, right? I mean,
if you have only pi 1, pi 2, there's no Jordan blocks.
If you have only phi 1s and phi 2s, it's diagonalizable, except if you start putting derivatives.
This existence of pi 3 is playing the very fundamental role.
Anyway, I think we should, we should probably, maybe a last question from, so you get, in fishnet, you get Jordan blocks once you couple derivatives into it, but phi 1 and phi 2 by itself actually happens to be diagonalizable, even though it's non-Hermitian. So Dima, you had
Well, I mean, there is a lot of similarities of what you're saying with crystal limit. I mean, crystal limit is not this singular twist limit. It is limit when Q, not your Q, but Q of XXZ deformation goes to infinity. It's called crystal limit. There are Cashewara bases, box ball systems, which have kinks, propagation rules similar to yours, but not exactly the same. Partition functions with another Q which you use. Counting of strings using KKT bijection. All these words, did you compare what you're doing with this combination? I mean, because it's a lot of, I don't say it's the same, but it's very like many similarities with this story. Okay.
I think we should proceed, but before doing so, let's thank Jangre one more time.
Thank you.
And wait, we have actually one more talk now before the coffee break. So Eli, can you?
on. Can you hear me well? Yes?
Okay. If you want to go to the next slide, previous slide, if you like to highlight something, do it with the mouse. So
or with, is there...
No, the people will see it
from
through
the
stream. Yeah?
Yes, okay.
And if you could stay behind the lecture, would be good for the
I
camera.
will try.
Okay.
I might not succeed.
Thank you.
So we are very happy for the next talk to announce Eli Pomoni, who actually started her career with, among other things, with integrability, and then in the meantime she has done many exciting things. But I'm very happy to see that you also still work on integrability and tell us something new today, right? Or
yes.
Yeah, wonderful.
Thank you, Matthias. And let me begin by thanking the organizers for having me here. It's great to give a talk again in person. So this stuff, I started in my PhD, and we were asking if the spin chain of n equal to 2 superconformal theories are integrable. And in fact, in one of the IGST conferences many years ago, I was bugging Kostas Zoubos, and I was asking him, because he knew back then how to do Q deformations, if we can maybe do something. So, you know, IGST was very important to start new collaborations, yes? So, and this is work with Randl Rabbe. Okay, I want to do this, I'm sorry. He graduated now, but we have other amazing PhD students. Enrico has a poster outside. You can go and ask him questions. And Hano, he's my PhD student from DESI, and Sinyu is a postdoc at DESI. Okay, so first of all, we stick to 4 dimensions. I'm sorry if your favorite number of dimensions is 3 or some other number. And well, n equal to 4 is integrable. This is what this conference is all about. And the question is, can we go beyond that in a nice, organized way? And okay, I have my little star here. If this is the only integrable theory, we know that it's not, but it's very sparse, the theories. We know that they are integrable. And again, I want to be able to, step by step, remove supersymmetry and see what will happen to me. And I hope I can convince you that we can do this in an organized way by the end of the talk. So first of all, in the past, and maybe there are still people here in the audience that believe that, people believed that the moment you go down to n equal to 2 even, integrability is gone. And why is that? It's my fault. We wrote this paper back in my PhD years, and we checked the Young-Baxter equation, and we found that it's not satisfied. And back then already we said that it's not integrable when we all got depressed. And nobody complained about that. Nobody complained in all of these years. But we can complain to ourselves. So let's, like in a very basic way, when we think about integrable models, how we should think. So there are rational integrable models like the XXX spin chain, right? And this has SU2 symmetry. And the moment you break a little bit by introducing a little bit of homogeneity, you get to XXZ, and you have a trigonometric model. And already there, you can find the quantum groups playing a role. But the moment you really break isotropy completely, naively you think there is no symmetry in the problem. But then, if you think again a little bit harder, you discover that there are elliptic quantum groups that govern what is going on. And in fact, there is even more than that, and there are many crazy papers that do this. There are hyperelliptic models. And in fact, if you really want to go all the way to study generic n equal to 2 and n equal to 1 theories, these will come up. Now, I want to argue why the Young-Baxter equation argument was just wrong. First of all, when you have an elliptic model, it really very much depends on the basis on which you decide to describe your model. So that if the Young-Baxter equation is the criterion or not, or something else, the dynamical Young-Baxter equation of Felder is the actual criterion. And for the people in this audience that the word dynamical takes them to Bizert, so this is not the same dynamical thing here. Now, the basis in which the elliptic model satisfies the Young-Baxter equation, we could think of it, we could call it Baxter. It's the Baxter-Bellavin R matrix that does that. But in that basis, we have Sklianin algebra acting on our states. And the moment you have Sklianin algebra, there is no highest weight states. But we are studying superconformal field theories. And superconformal field theories have BPS operators. And BPS operators, when you map them to the spin chain states, are highest weight states. So it's simply wrong to think that you are in this basis. So it's simply wrong to think that the Young-Baxter equation is a criterion. Is everybody happy with this? So this is where we start from. So this argument was just too naive. And this is the correct way to think now. Fantastic. Now, you know, mathematicians, of course, know more than us. And there are much richer structures than elliptic models. And in fact, already from Drinfeld, we know that the moment you have a Drinfeld twist, you can construct beautiful quasi-Hopf algebras. And they come with even more advanced quasi-Hopf Young-Baxter equations. And here is how it looks. So there is a lot to play with. And I will try to show you that this is what we have. And then if you want to ask the question of integrability, the way to do it is you ask if your Drinfeld twist obeys a certain cocycle condition, and if it does, your model drops down to a dynamical Young-Baxter equation, and it's integrable in the elliptic way. Yes? And by the way, if your model is hyperelliptic, we don't even know what is the criterion. But one should do this derivation again from scratch. So this is a little bit to set the scene where we are. Now, OK, n equal to 4 super Young-Mills, the moment you say, well, I want to do SUN, the theory is unique, you have a coupling constant, that's it. But for n equal to 2 theories, even for the superconformal ones, there is a landscape of theories as long as you want a Lagrangian description, but they are classified, and the classification is in this paper. And for most of them, the way to obtain them, and this is like as an exercise in our mind, this is really the best way to think. You should always think that we take n equal to 4, an orbifold, and then you marginally deform with all the possible marginal deformations. And this is the way to create most of the landscape of n equal to 2 theories. Yes, and this is a fantastic organized way to go for it. And because of that, because of the orbifolding procedure, we actually know what the gravity duals of these theories are, so we can also do Adscft. And we also know that at the orbifold point, so when these coupling constants are all equal to each other, we also know that these theories are integrable. So the only thing we need to learn how to do is we need to understand what marginal deformations do. That's the only thing we need to understand. So here is the main example. So if you are an n equal to 4 super Young-Mills person, it would be nice. If I had a blackboard, I would like transfer some of these things on a corner so that we cannot forget them. But it would be nice to try to remember a little bit from this slide. So the main toy model here is an SUN cross SUN gauge theory. So here are the two color groups. They have fields in the adjoint representation. These are scalars. And there are also fields that are bifundamental. And the way you get them when you orbifold is you originally think that you have x, y, z. These are the n equal to 4, 3 scalars. And after the orbifold projection, some of their elements go to 0, and that's how you get the bifundamental or the adjoint matter. Yes? And when this is G1 and G2, the coupling constant of these color groups, when they are equal, this is when we have the orbifold point. So this theory is enough to study and discover, first of all, something that I will try to show you in the coming slides, that the spin chains of these theories, the correct way to think of them is that they are dynamical. And from that, elliptic or hyperelliptic, all of the other things come. And another thing that maybe many people ask, so I just say it from now, so we are done with it. If you want to study super QCD in the Venetiano limit, you should first understand this theory and then take the limit of one of the two couplings to go to 0, and then you win. That's the only organized way to really succeed in playing this game. And if you don't believe me, you can ask me afterwards why this is the case. Okay, so now we go to the technical stuff. Let me summarize what I will do. First, I will talk to you a little bit about one-loop spin chains, because it's very important that we organize our mind for how to think about the Hilbert space. And I will try to show you in a very basic way why they are dynamical. And then I will concentrate on the quantum symmetries. So the main thing for this talk is that I want to show you that we have a quasi-Hopf symmetry algebra. I want to show you that it's very easy to read off the R matrix in the quantum plane limit and get the twist, the Drinfeld twist. And then once we have that, we basically need to understand it. And we will have a coproduct with which we act. And then we can see how our spectrum then gets organized in multiplets of this quantum group. So this is the plan. Are there questions? Okay, then let's go. So first of all, one loop dynamical spin chains. First, let's start with something very easy. And this is this xy sector. X and y are the two scalars that after the orbifold projection, they are bifundamentals. And because of that, most of the people in the audience should like this sector very much because it looks very much like ABJM. So it is actually an alternating spin chain. And the good way to think about it in the dynamical language is you start from an n equal to 4 state. I think that I take the trace and I cut it open and I have an open state. Yes? And the moment I do that, the only thing I need to do extra to specify which one of my states is my n equal to 2 state, I only need to specify for you the first open gauge group. And the moment I do that, the rest is dynamically specified by following the color indices. There is nothing else I need to do. So no, at this stage, I will always cut and open my chain and study open chains. And only in the very end, I will glue things back. I mean, this is also how we do most of the things for n equal to 4, so let's also do it here. And here is my little Chan-Paton label that tells me what is the first open index. So all n equal to 2 states can be labeled in this dynamical way of thinking. Yes? So this is an alternating spin chain, and actually this is maybe in some ways too much notation. But the moment you do that, you already start seeing nice things happening to you. And one nice thing is that okay, back in the day, we were writing the Hamiltonians in this way, and this is the Hilbert space. But now when you go to the new dynamical language, here is the new dynamical language, you can see with your bare eyes that in fact what you have is an XXX Hamiltonian, but you have it with a different coefficient depending on which of the two dynamical states you act. Yes? Here there is this 1 over kappa. By the way, kappa is the ratio of the coupling constants, and here is with kappa. So what do we have? We have a dynamical XXX spin chain. And the way these two XXX spin chains couple is dynamically determined by the basis, by the Hilbert space. Let's now do something a little bit harder. So let's involve fields that are in the adjoint representation. Then we cannot be alternating anymore. It's more interesting. And the moment you have these z's going twice, the fields in the adjoint, you can... Sorry, loud. So if they are two different sectors, the way they are different sectors for n equal to 4 super Young Mills. I choose my R symmetry. So yeah, this is a little bit the problem. I want you to try to remember this slide. So when I write phi 1 and phi 2 or z, these are in the adjoint representation. And this index tells me that this is adjoint in the first color group, adjoint in the second color group. Here, these gadgets, they have two indices, 1, 2, And this means that this is a bifundamental guy that starts from here and goes here. If I have 2, 1, it goes back. That's the notation. Good. Here. So again, a little bit harder, but still the same principle. What is the principle? I take the n equal to 4 state, I cut it open, I specify the first color group, and these are my n equal to 2 states. And here is how we do it in a dynamical language. We just specify the first open color index. That's it. And then we go and we look at the Hamiltonian again, and we write everything beautifully in the dynamical notation. And what do we see? We see this is the temporally lib Hamiltonian. And you know, the one from the other, the only thing that they differ is that this kappa goes to 1 over kappa. So we have a dynamical temporally lib Hamiltonian. That's what we have. Yes. Dynamical refers to the color index, if you wish. Yes. How? So the Hamiltonian always is defined on which, let's look at here, which element specifically of the Hilbert space it acts. They do speak to each other, because if this is Q12 and this is Q21, when you have Q21 and you want to act to the next guy, you move to this. So they do speak. So your chain is not only 2 things, it's many things. And if this is the first and the second guy, then this can be the second and the third, and so on. So they do very much speak to each other. Yes? If the Hamiltonian was the one for the y sector, what you say is perfect. If we go to this sector, where you have the z's, and they can be as many as you like, you lose this ability to do that, and it's truly a dynamical, full-on dynamical. And we have to live with that. I mean, okay, the truth is that now I could start a whole talk that I am not going to do, how this goes all the way to Felder-like models. And to maybe to some people's disappointment, I won't do that because I want to talk more about the quantum groups. But let me say some words about that. And this is, all of that is in this paper. So first of all, this is a very old idea. So this looks like you have trigonometric models that somehow you put them together, you know, a trigonometric model with deformation parameter kappa, a trigonometric model with deformation parameter 1 over kappa, and somehow you put them together. And in fact, not even here, this goes back to Fatev and to Takhtajan, like Leningrad Integrability school, that you can make elliptic model by averaging trigonometric models. But a very beautiful way to think, especially now that I have introduced this 1 and 2, is to go to Felder and think that his dynamical parameter, in fact, does precisely that, keeps track of the color group. Of course, this is not quite Felder because of this adjoint field. And what this adjoint field does, it doesn't change the dynamical parameter. So what we actually have is a restricted solid-on-solid, or better, cyclic solid-on-solid model. And I will just say that this is a result that I will not explain at this stage. If you want to study the holomorphic SU3 sector of these chains, we have explained in this paper that this is captured by a dynamical 15-vertex model. And this is a very beautiful story to study in the future. Okay, but I continue. Okay, now let's go to the symmetries. Because if you want to understand integrability, better first to understand the symmetries of the problem, right? So, first of all, how are we going to discover these quasi-Hopf symmetries? First, I give a quick summary, and then I go into it and I explain. The way you discover it is basically the same way people discovered how to study marginal deformations of n equal to 4 super Young-Mills. And what you do is you begin by looking at the F terms, or the superpotential of the theory. And the moment you have these define complex quantum planes. And by having the quantum planes, you immediately can write down the R matrix. The R matrix, in my baby language, is basically the moment you plug in the matrix in this eigenvalue equation, you get the quantum plane back. And this is enough to check that superpotential is invariant under quantum group and all the other things that I will do with the BPS states. So let's start doing it, and let's start with the most baby example possible. So let's take two coordinates, x and y. This is the famous Manin quantum plane. And okay, we open a quantum book and we copy the R matrix and we plug it in here and we say, okay, this is how I get my quantum plane back. But what is very interesting is that now we can discover the symmetry transformations of this quantum plane. And here are the symmetry transformations. When I put x1, I mean x, and when I put x2, I mean y, right? So how do I get the quantum group? I just take my R matrix and I plug it famously in the RTT equations, and I get the algebra. That's how we do it. So let's now go to what we need. So what we need is we need three-dimensional complex quantum planes. And these are classified mathematicians. And the mathematicians tell you that if you want to do that, you need to know two tensors, this E and F, with three indices. And the moment you know these two tensors, these define the quantum plane and the quantum coplane. And the moment you have them, you can plug them in these equations. C is just a constant, and you have your R matrix. And this is the R matrix that when you plug it in the RTT, it gives you the quantum group. That's how we are going to do it. First of all, before I say how we will do it, let me remind you that this is how it was done for the marginal deformations of n equal to 4 super Young-Mills. So either you write down the F terms, which define the 3D quantum planes, or you just look at the superpotential of n equal to 4 super Young-Mills, you write down the List-Lassler, and you ask, what do I need to replace the Levi-Civita simple with which tensor? And this is the E and the F that the mathematicians need in order for us to write down our matrix. And you can write down the R matrix, the Hamiltonian, everything, and you discover there is a quantum version of SU3 that leaves this Lagrangian invariant. Now, before we go to the theory, I want to say one more thing. We understand this, in fact, from the Adscft also. And how do we understand it? Well, in the gravity dual, when you have a B field that is turned on the transverse 6 dimensions, what happens is that you just read Seiberg-Witten, and what they tell you is that when there is a B field and your open strings end on the D3 branes, they see a non-commutative geometry. So this non-commutative geometry is the quantum plane. So these open strings see precisely this quantum plane. And for the List-Lassler, this was done by Manuela nicely. And I mean, if you want, you can read our paper for how to do this for the orbifold. Okay, now let's really say what is this structure. So here, for the Z2 quiver theory that I showed before, here I write the F terms. They come into two chunks because it's a Z2 orbifold, so there are two images. So there is always this thing with the two images. And the way I read off my E and F tensors is that I replace the Levi-Civita of n equal to 4 with whatever is needed so that I get my correct n equal to 2 Lagrangian. And here is written what is needed. And the moment you do that, you have an R matrix. For the XY sector, this easier alternating one, you basically get the identity, which is great. And for the other two SU2 sectors, which are these more truly dynamical ones, you get a non-trivial R matrix with the property also, if you look slightly closer, that this with this is kappa going to 1 over kappa. And the fact that the XY sector are matrix proportional to the identity. What does it mean? It means we have an SU2. And yes, we know we have an SU2 because this is the SU2 symmetry of n equal to 2 theories. And the XZ sector, the fact that it has this non-trivial R matrix is precisely because this SU2 symmetry naively is broken. But what I'm trying to tell you is that it's not broken, it's upgraded to a quantum SU2. And okay, here is the R matrix again. You can plug it in the RTT relations, and you precisely get SU2 kappa quantum, yes? And on the top of that, by splitting the R matrix in this way, you in fact get the Drinfeld twist. So you actually have a full-on quasi-Hopf symmetry algebra defined basically by this Drinfeld twist. So up to now, everything is beautiful, but it's somehow very formal, and I can say that I almost don't like it. I want to do something very concrete. So let's do something very concrete. I want to make multiplets. If we have a symmetry, we should be able to make multiplets. So the point is, let's try, we have our beautiful twist. Let's try to write down a coproduct with our beautiful twist in such a form so that we can actually act with our naively broken generators and see what happens. So the moment you do that, the moment you have such an action, you can first of all ask, is my Lagrangian invariant? Is my superpotential invariant? And the answer is yes. It is indeed invariant under an SU3 kappa deformed, precisely the one that I get by embedding these SU2s. And not only that, what we can in fact do is that we can construct, by acting with these broken, at least naively broken generators, we can construct SU2 kappa deformed and SU3 kappa deformed multiplets. And we can see, for example, that the BPS spectrum organizes into multiplets of that. And let me show you examples. So if you have ever studied a tiny little bit of n equal to 2 theories, you know that, for example, this state here, where it's like the adjoint scalar of one color group, and this state here that looks like some type of baryonic state, they live in completely different n equal to 2 superconformal multiplets. But if you act with this broken, with our new coproduct generators, you can in fact make a multiplet in which all of them live. And not only that, all the states in the middle, you can all get them by diagonalizing the Hamiltonian. And not only that, this coproduct precisely reproduces a very precise prescription for all the coefficients inside the operator, which is reproduced by diagonalizing the Hamiltonian. This is actually quite fascinating. And you can do this for SU2 multiplets, and you can also uplift it for SU3 multiplets, but I didn't want to draw an SU3 multiplet here. Another really cool thing, because you know, okay, SU3 holomorphic, at some point we had a real fit, and I was like, maybe there is something wrong. So I really wanted to embed everything to the full SU4, because then you also get non-holomorphic things. So for n equal to 4 super Yang-Mills, we have the stress energy tensor multiplet, right? And the bottom of it is the 20 prime. So here is the 20 prime in an n equal to 2 language written. And the green lines, you can see them faintly. They are SU2 generators, so they are really there and they are unbroken, and we have them. But the blue generators are all broken naively, and this is not a multiplet. However, if you use this coproduct, you can reproduce this whole multiplet. So what am I telling you? I am telling you that the n equal to 2 spectrum lives in kappa deformed n equal to 4 like multiplets. Any complaints? Sorry? So this statement, you could call it an one-loop statement. So at this stage is BPS. It will stay, yes, it will stay. But of course, what we want to do is we want to use something like this for everything, right? So what I can show in almost, yeah. Okay, good. So first of all, let me make a conjecture. So my conjecture is this, that if you have a theory with less supersymmetry than n equal to 4, that you obtained by doing something like orbifolding, I think orientifolding, all of these procedures go the same way, from the mother n equal to 4 theory, it will enjoy a quantum deformed version of the PSU2, 2/4. This is my statement. And all the naively broken generators will be basically upgraded to quantum generators. And let me try to visually put it in your head. So when you have less than n equal to 4 supersymmetry, what you need to do is you look at the F terms. They are not defining anymore simple planes. They define quantum planes because they are sprinkled with all the coupling constants. And from them, we can read off the R matrix the way I described, and we get what is the quantum group that acts on them. And precisely the way I described, from the R matrix, we read off the Drinfeld twist, and from the Drinfeld twist, we can have everything that we ever wanted that the quasi-Hopf symmetry algebra has. Now, first, let me say where we currently stand. So first of all, I described everything for this Z2 quiver, but we equally well can do everything for any A-type orbifold we worked out. Of course, I am pretty sure whoever wants can do a T-type orbifold or E, or, I mean, it just depends on the pain you want to go through. We are currently working out more multiplets. So basically, I want to have Dolan-Osborn, the whole thing, I want to have it, you know, quantum deformed now. So here is maybe for the question. So what we have now is we did states with length 2. So when you do 6 times 6 of SU4, you have 1 plus 15 plus 20 prime. 20 prime is the protected, but 15 is a guy, 15 and 1 are not protected. Okay, 1 is not quite a multiplet because it's just a singlet, but 15 defines a new quantum multiplet. And this is not protected, yes? And then continue. Okay, I already mentioned that there is this 15 vertex model, that this is very important. Another thing that I didn't mention, which is also very important, is we have an explicit coordinate Bethe-Ansatz in the previous paper. And you can see immediately all the elliptic happiness coming in. This is a one loop result. When I show this to n equal to 4 people that they know this, you know, to all loop, to say that this is a one loop result is pretty amazing, I think. And of course, you can do this with the scattering matrix and everything. You really need to use theta functions to do the work there. And there is a brute force computation. I mean, Anna will show later some amazing things that they are doing with Marius. And what they are doing can be imported to study these things very nicely. This is one loop. You use the one loop dilatation operator, you act, you do the coordinate Bethe-Ansatz, and you get this type of square root. The ratio. So, sorry, what I am doing here is that I have, in this formula, I have G1 over G2, and as long as they are finite and between 0 and 1, I am fine. Yes? So this formula will remain. It's really weak coupling formula. No, because this is a one-loop formula. I mean, I can try to derive the same formula. So with Christoph, for example, we already have a 3-loop Hamiltonian, you know, like. But the amazing thing is that it's already elliptic. That's my point. Yes, and where we are going, so actually with this spectroscopy that we are doing now, the moment in fact you study 2 sites and 3 sites, you can already formally answer the question of integrability. Of course, maybe you can say that this is a useless, but for me it's the most important thing. I want to say yes or no. And all you need to do is, we really need to very carefully write down all of our multiplets, and then say the twist between 3 sites, the twist between the 2 sites, what is the cocycle condition? And this will answer this question. So this is happening, and this hopefully will happen soon. And then all the things we love from n equal to 4, they can go through. They can just simply go through. And also n equal to 1 theories, as long as we have a nice description that we start with D3 branes and some conifold, orbifold singularity, something, everything goes through. And okay, this is more like a, so at some point, I don't know, I am definitely very interested, but there are experts in this audience that they are really good with the gravity side. So we really need to do something about the gravity dual and start calculating there. Yes, so please, I want to recruit people. And there are also 2 other very interesting things. So Francesco is somewhere there. We really need to generalize these works of the dual of free n equal to 2. We really need to see the quantum string coming up. And something very similar also should happen with the Chern-Simons approach. Yes? Bogdan, yes.
Questions?
It's not on, most probably.
Ah, all right. Okay. I wanted to understand better what you were saying about the multiplet, the 20 prime. So my understanding is that you have the multiplet, and now you can move through this arrow through some quantum group operator, which is not the usual algebra generator that you would have in PSU 2,2/4. And then I presume that when you go from one level to the other, your dimension will increase, but not by half, by something else that you can compute. Is that?
So let me say slowly what this thing is.
Okay.
So first of all, I said it, but let me say again. These arrows are generators that are truly there. They are the SU2R symmetry generators of n equal to 2. So in this direction, nobody can stop you from moving, even with the old knowledge. So this is Dolan-Osborn. The new stuff is the blue arrows. The blue arrows are the generators that are naively broken because the orbifold broke them when you came down from n equal to 4 to n equal to 2. So these were generators that existed only in the n equal to 4 theory. They are SU4 generators. Yes? And now we have this new coproduct that takes these SU4 broken generators, it sprinkles them appropriately with kappas, and it does whatever it needs to do to them. And the moment you have them, you can in fact, this is a calculation, it's not a drawing.
Yeah,
you have this operator, you act with this coproduct on it, and you get this operator.
But
you act
my
with
question
the
is,
coproduct, and you go down.
Can you compute from this action of the quantum group, can you compute the dimension of the various operators that you have in this diamond? Because normally it's very easy, right?
What do you mean that I can compute explicitly the whole picture, like arrow?
Normally I know that when I go down with one of these arrows, which would be, I guess, a supercharge, in the usual deformed case, delta minus j increases by a half. In the deformed case, it should not increase by a half.
You can define the same thing. You can define the same thing.
My point is that normally I would expect these things to get an anomalous dimension, right?
Okay, so this is a BPS. So maybe this example
Well, it
is not
shouldn't.
good.
It
So
shouldn't be because you don't have the...
Wait, good. So when this is not a BPS state, so when if...
No. This whole multiplet is no longer BPS.
Yes, so if this was not BPS, but it was, let's say, the 15...
No. In this case, you start from something that used to be BPS, but is not BPS anymore, right?
No, this is BPS.
Then I'm afraid I don't... I mean,
So
even
these
in the normal, like
operators...
beta deformation and so on, these guys
Wait,
get
wait,
anomalous
maybe
dimensions,
you don't
right?
understand. Wait. So this, for example, this operator is the famous Coulomb branch operator of n equal to 2, and they form a chiral ring, and they are BPS and forever protected. These are mesons, and they are in the multiplet of the flavor current of n equal to 2 theories. So these are also known to be protected. This thickly graphic is also another protected, known to be protected, is the chiral primary of the stress energy tensor multiplet of n equal to 2 theories. So all of these gadgets are all known to be protected, and they have all the same anomalous dimension equal to 0.
I see.
So clearly, the energy of all these babies is 0, or anomalous dimension. What changes as you move is these quantum numbers here.
I see. And in the case where you started from a different guy, then I'm a bit confused because there are descendants of the vacuum in n equal 4 superior Mills that once you, let's say, turn on an orbifold or a beta deformation are not protected anymore. And they are still descendants of the vacuum.
Yes, very good. Let's go slowly.
But not of the 20 prime of longer, like 3
Yes,
to
so
the J.
first of all, one very sad thing in life is that nobody worked these things out for the beta deformed. And I think I'm going to wait a couple of more months, but if nothing appears, I will just do it. So my conjecture is that you should be able to do this for the beta deformed.
I don't think so, but we can discuss it later.
Yes,
but
I think so.
The argument is that the jump in anomalous dimension of these guys that used to be BPS but are not anymore is something very...
So I think you are confusing different things.
Okay. Okay, we can
so
discuss
the mesons and all chiral operators, first of all, it's clearly they are going to, so also n equal to 1 theories have chiral rings. So this multiplet, apart from maybe these guys for n equal to 1 theories, are guaranteed to be protected because they will be in the chiral ring, and this guy is the stress energy tensor. So they are guaranteed by n equal to 1 representation theory to be protected.
Okay.
Burkhard?
Just on Alessandra's point, I mean, I know, for example, if you take like the length 3 or length 4, and you have the manifest in beta supersymmetry, then of course you will have these properties. But as soon as you go transverse somehow, the anomalous dimension is just going to be order beta squared, right? I mean,
sorry, wait, what do you mean when you say you go transverse?
I mean, I don't take the manifest symmetry and beta deformation, but I sort of take some other direction, which should be quantum according to you. Then you will get
I don't understand what you want to do. Sorry.
You have n equals 1 supersymmetry, which is manifest from the n equals 4, right? And beta deformed.
So what you need to do is you take the n equal to 4 multiplet, whichever one you like, you decompose it the way Dolan Osborne tells you into n equal to 1 multiplets. This is very easy. Naively, you think they are all broken and they should never talk to each other. But what I am trying to tell you is that if you define a coproduct in this form, if you can do this, of course, in this case, we can explicitly do this. If you can write down such a guy, then you can fill in the gaps.
All I'm saying, what I know essentially is that take a state which is like a Z to the third, fourth, whatever. You don't even have problems with this length 2 stuff in beta. Yes. And act with anything which is not the manifest symmetry. Then you will create states which have anomalous dimension that have sort of beta squared plus blah, blah, blah.
Question, do you do this for the beta deform or for the gamma deform? Because gamma deform is not supersymmetric.
Let it be beta. I mean, we were looking at beta.
Then we should talk for precisely the way you write things down, Because in our case, there was a tricky point that for me, it took basically a couple of months to understand how to do this guy. And what was the trick? Okay, I say it openly. So you need to change the boundary conditions of your open chain. So you can always, for example, when you compare the temporally lib with the XXZ, they are not the same Hamiltonian, right? But if you want to discover as you do quantum, you need to use the temporally lib Hamiltonian. And the difference from the one to the other is different boundary conditions that you impose on the open chain, that of course after tracing, these things are gone. Yes, so maybe this is the problem.
Well, I know that I was sort of critical about the same point when you gave the talk in our place, but a few months have elapsed, and maybe
yes,
you can...
so the few months is precisely this guy.
Please tell us.
Yes, yes.
Okay, thank you.
Yes.
Okay. Dima was first.
Actually, now I understand that I missed point when you showed why it's integrable.
Well, I didn't say why it is integrable. I said that this is not in this talk. In this talk, I only want to understand the quantum symmetry. And the only way to find the final answer, I don't have it yet, the final answer is here. So the moment these things are done, completely perfect, then you ask this question. When you have the twist for 2 sides, 3 sides, you write out explicitly the cocycle condition that takes you from 2 to 3, and depending on how it looks like, it can be integrable, yes or no. What it is definitely is it is quasi-Hopf. For maybe I show here. I had it at the very beginning.
No, maybe I can clarify slightly. So for n equal 4 super-Young mills, integrability not super conformal, but it's Youngian.
Yes. So now it will be a quantum elliptic.
So you showed for the moment only deformation of superconformal algebra, but Youngian version of
no, I don't have it. Yes.
But do you was it somewhere hint when what you should check? Maybe I didn't.
No, nothing is hidden. In order to really show which precisely quantum toroidal algebra this is, you need to first understand this.
Okay.
So this is not done yet. Okay. This is coming.
Okay, there was one more question here. Maybe the last question, actually.
Thanks for the nice talk. I was wondering if you had a 3-point function, let's say, which involved epsilon.
3-point function I don't have.
3-point function with some with epsilon 2, and you wanted to compute the 3-point function with d in this super multiplet. Can you use this operator that goes from...
You want to do bootstrap now?
Well, I'm just wondering, does this operator that goes from epsilon 2 to d2 allow you to compute?
Yes, so you want to do bootstrap, so amazing. So once this is done and we believe it, we need to basically take what you are doing and define the quantum blocks of the quantum PSU2,2/4, and then we can do bootstrap for that.
But okay, I'm asking maybe a more basic question. Like if I had n equals to 4 supersymmetry, I would only have one OP coefficient for this whole diagram. And here, would it be some integral transform that takes me from the 3-point function involving epsilon to the 3-point function involving d, or?
But you need to know the OPE, right? You need to do something with this. So, nobody knows anything. It's the first time anyone says these words now. So we need to take these words and make them everything else that we know for n equal to 4. We don't know. So up to now in our life, we either do n equal to 4 super-Young mills and we use the n equal to 4 superconformal algebra, or we do n equal to 2 and we use the n equal to 2 superconformal algebra. What I am saying, we have to do everything from scratch again.
Thanks.
Okay, I think I see no more questions. So let us reconvene at 5 o'clock. So we have a nice break, but let us thank Ellie one more time. So welcome to the final talk of today. We have Anna Retore from Dublin, and it's a pleasure to introduce her. She is, I guess, a newcomer to IGST. It's her first time in IGST, and is also, I would like to point out to the organizers that it's very good that you, in the end, you stuck to this other tradition of IGST, that you have a lot of many young speakers. That's wonderful. And Anna is certainly one of them, and we are very much looking forward to your talk.
Thank you very much. So thank you very much for the organizers to invite me. I'm very happy to be here, and my first time at IGST. So today I will talk about lifting integrable models and long-range spin chains. So there are many applications of integrability, as we all know, especially in string theory. We have many of them. And in recent years, many new ones appeared in condensed matter in particular, like these open quantum systems. There is some systematic construction now for them. Also in quantum computing, they are starting to try to do a few things. So there are new applications also appearing. And we have this huge box of tools that integrability provides. And in the recent years, this box of tools has been increasing as well. Like we have now quantum spectral curve, hexagons. So we have many nice techniques that we can apply to integrable models and many nice applications. So I believe the questions to be able to reply, like to look to a Hamiltonian and to say if it's integrable or not, remains a very relevant question. To be able to classify integrable models with a certain ansatz is also a relevant question, and also to be able to systematically construct new integrable models. So this is what I will talk about today. And of course, there are like a lot of work has been done on this subject. For example, the algebraic method is by far the most successful to find the integrable models. Like lots of models were classified in this way, in a very systematic way. And in particular in Adscft, most of their matrices that were found people used this method. And a very important part of this method is to have a symmetry, like Yangian, for example, then you can use it. And, but you cannot apply it if you don't have a symmetry. So there are some limitations. But if you can apply it, it's very nice. You can solve linear equations to find their matrix, so it's very, very effective. There are some other methods, just to cite a few, like you can directly diagonalize the Yang-Baxter equation by applying a derivative on the equation and solving some differential equations. This can be quite hard for some classes of models, but you can do for a few classes. You can also expand their matrix and try to resum at some point, like in terms of, you can expand in terms of the spectral parameter and the Hamiltonian and try to resum at some point. And these are all very nice. They all have very good advantages and a few disadvantages. And today I will present two different ones. And they also have some advantages in comparison with these and some disadvantages. And I'll try to argue why they are interesting and useful. So the talk is divided mainly in two parts, like the two methods we will use. The first is this boost automorphism method. This is about a project with a few projects with Marius, Chiara, Anton, and Paul at Trinity. And this is applied, it can be applied for nearest neighbor spin chains. The second method will be able to apply for long-range spin chains. It can actually be nicely, very easily applied for long-range spin chains. And I will show two examples. We computed the three-loop lax operator and the R matrix for the SU2 sector of n equals to 4 supreme mules. And they range 6 vertex deformations using this method. This is a project I did with Marius at Trinity. Okay, so let's start with the first method. So this boost automorphism method. So the goal here is classify integrable models that satisfy regularity. So when you have that both spectral parameters are equal, you have the permutation. And you want the logarithmic derivative to be your Hamiltonian. And we will consider for the purpose of to classify these models the periodic chain. So nearest neighbor interaction, a periodic chain. So it's very relevant to do this distinction of difference and non-difference form for our method. So difference form is usually when you can write your matrix as R of the difference of the spectral parameters. All the relativistic models are in this class, and if you have this type of our matrix, your Hamiltonian is constant. This is because of how this is defined. So your Hamiltonian will not depend on the spectral parameter. And the second type is non-difference form. And this means that you cannot write the R as depending on the difference of the spectral parameters. This case is usually much harder to classify just because it's harder to solve the Young-Baxter when you have this structure. There are not so many models known in comparison with the first class. But the ones that are known are extremely interesting, like Hubbard model is in this class, for example, and the ADS models, like in ADS2 and ADS3, they're all like this. So it's useful to be able to classify them. Okay, so let's say we start with some ansatz Hamiltonian. I just put some 6 vertex here just to exemplify, and let's say, so for now we are saying that it's depending on U. So, I forgot to say, so here, if our matrix is of non-difference form, your Hamiltonian will depend on the spectral parameter, so it will not be constant anymore. So, let's say we start with some ansatz Hamiltonian, and we want to be able to say if it's Young-Baxter integrable or not, or if you want to classify all these, the Hamiltonians with these ansatz that are integrable. Of course, for these ansatz, we know, but it's just an example. We actually found some interesting things even here. But, okay, so we want to solve Young-Baxter. Let's say we start by applying a derivative with respect to U, and then we send V to U. We could, in principle, try to solve this. It's very hard. It's that method I mentioned before. But we could also put these conditions we know here, these conditions we assumed at the beginning, and we will get what's called a Sutherland equation. And let's say we would like to solve this equation. The hard part here at this moment is that we don't know the Hamiltonian and we don't know the R. So we have these differential equations with too many unknowns, and it's, especially for non-difference form, it's very hard. So the ideal would be if we knew what this Hamiltonian is, what this Hamiltonian could be, if we had some clue, like some hint about the Hamiltonian, we could do much more. It would be much easier to solve. So the question, like, do we have an independent way to solve to say if this H is integrable, or let's say if we can put some extra conditions on this H from the beginning. And for that we can use this boost automorphism mechanism. The boost is very nice because you can use it to generate higher charges starting from a smaller charge. So if you have a charge like QR, you can generate QR plus 1 just by commuting with the boost. So this is very useful. So you have a kind of an independent way to construct your charges. So what we do here, the first step is like we start with some ansatz and we generate Q3 using the boost. And then the first step for integrability is that Q2 and Q3 have to commute. So here, if you want to classify the difference form case, we can start with a constant Hamiltonian. And then to solve this equation is basically to solve a system of cubic polynomial equations. You can put on Mathematica and solve it. And if you're interested in non-difference form, you have now a derivative that will contribute here. And because your Hamiltonian is U-dependent. And you have to solve now a system of differential equations instead of just the cubic polynomial equations. But let's say we did this. So we now have some Hamiltonians that are potentially integrable. So they satisfy Q2 with Q3. So, but in principle, we need all the other commutation relations being satisfied, not only Q2 with Q3. But let's for now to assume that Q2 and Q3 is enough. and substitute it on the Sutherland equation. So we did that for several classes of models, and then we solve it for the R matrix. So when you do this, it's much, much easier than before, because now you just have to solve these differential equations, the system of differential equations for the R, not for both R and H at the same time. And actually it was enough. So Q2 with Q3, so for all the systems we tried to classify, Q2 with Q3 was enough. We never found an extra condition on the Hamiltonian. So we always managed to find an R matrix just with the conditions that we had found from the Q2 with Q3. And this is actually quite under control. So you can, even for non-difference form models, you can do a lot actually. So it's quite nice. So we're quite happy about it. So the summary of the idea is that we start with some ansatz for the Hamiltonian. We compute Q3 using the boost operator. And then we require that Q2 with Q3 commute. We solve this system of polynomial order of differential equations. We find these potentially integrable Hamiltonians. We can just substitute this on the Sutherland and find the R matrices, and then we check. So this was applied for many cases. So at the original paper for difference form, Marius, Paul, and Anton, when they did the first paper, they applied and they found all 4x4 difference form models. They managed to classify all of them. And then on the we classified these SU2 plus SU2 R matrices for both difference and non-difference form. And for this case, you find several new non-difference form models, and all the ones that were known. We also managed to find the new integrable deformations of ADS2 and ADS3 as matrices. And this includes an elliptic deformation, which is quite interesting. Like it's an elliptic deformation that interpolates between ADS2 and ADS3. So we know you have some elliptic function. It depends on elliptic functions, and when k goes, like the modulus of the Jacobi functions, when the modulus goes to 0, you get ADS3. But when the modulus goes to infinity, you get ADS2. So it's quite interesting. But also, Marius, Chiara, and Balázs applied this method for Lindblad systems. So these systems, you take into account also the contribution of the environment. So they have, so there were several cases that were known to be integrable for these Lindblad systems, but there was not a way so they were always checked to be integrable, like some known model was, this was, they did the first systematic construction for these systems. So the method seems to be nice. So we managed to, for the ansatz we tried, we managed to find all the known models that should be there, and several new ones. And it's relatively easy to apply. So when you don't have much symmetry, you can still apply it in comparison with other models. And it's particularly effective for non-difference form. So in principle, we are very happy. But there are some disadvantages always. So what we expected when we started was like, let's classify the models, and we find, let's say we find a few interesting solutions. What happened in practice was that we found lots of dependent solutions. And this is because you can transform the R matrix in certain ways, and this will preserve Yang-Baxter. So there are several types of transformations you can make on the R matrix that would preserve Yang-Baxter. And we have to find a way to distinguish this, and like the method generates lots of dependent solutions. So we need, and you can kind of apply these transformations in different orders. So it's quite hard to, like for simple models, for the cases we solved, they were quite manageable. But if you try to put, to crowded R matrices, or like, you can, at some point you start to have a technical problem to how to distinguish this. So it's a lot of work to make this distinction and separating groups and say, like, just keep one. A second disadvantage is that, okay, we are trying to, if somebody gives you a Hamiltonian and asks you, is it integrable? And this Hamiltonian they give you is constant. Sometimes you try and you say, oh, it's not integrable. But it could be that when somebody gave you the Hamiltonian, they had chosen, like for some physical reason, the value of u was chosen. And this Hamiltonian originally was, like, there exists a Hamiltonian that will be integrable, but it will be u-dependent. But you don't know that because somebody just gave you a constant Hamiltonian. So you would reach the wrong conclusion for these cases. So this is a problem. And since we don't have this u-dependence, so for small cases, you could try to put an ansatz and classify. You'd have to classify all the cases of that structure to be able to see if the particular one is there. So if you need something that's a bit larger, this becomes very hard to do. And the third problem is that we were not able to generalize these for long-range spin chains. So this brings us to the second method, so where we try to solve these problems. And the main question we want to solve here is if somebody gives you a constant Hamiltonian, can I say if it's integrable or not, independently of if it could be u-dependent at some point or not? The answer is yes, and I will explain now why. So it's well known that you can define your transfer matrix as this product of lax operators. And then your charges are just, for periodic chain, they are just the logarithmic derivative of the transfer matrix. And you have this RLL equation, so all this is very standard. So for the method, we will start now, like always, with a constant Hamiltonian. So I put here this example is just some 6 vertex Hamiltonian, like 5, like this, yeah. It's still nearest neighbor at this point, so I will explain the method for nearest neighbor first, and then to say how it is modified. So we still consider periodic chain and regularity, but always constant now. So the way we start is like we expand the lax pair like this, in such a way that you will have the Hamiltonian here, and we put this like everything explicit. All the u-dependence is explicit there, so all these Li's are all constant. So we'll take this expansion. So it's something very simple. We were taking some expansion. We are putting on the transfer matrix, and we are computing the charges. So the first thing we compute the Hamiltonian, and then we compute Q3. So, but we will always keep only the first term, because if we want Q2 with Q3 commute, this term will always commute already with Q2, so it doesn't contribute. So it's just much easier to do the method very fast for many orders if we forget these terms, because they never will contribute. So, because they are not relevant for the commutator. So for this specific model that I put the example, if you solve this, you get only one condition. So at this, from Q2 to Q3, so if you remember here, we had 6 objects here, and only one of them is fixed by Q2 with Q3. If you go one more order, like if you compute Q4 now, like this, ignoring all the rest of the terms, and you require it to be 0, you again can find a condition for L6. And if you keep going, you can always solve for this L6 element and forget the rest. The other ones are free. So you can basically choose them. So you can keep doing this, and like you fix, like when you commute Q2 with Q5, you fix L6 4. And if you do Qn, Q2 with Qn, you get L6n minus 1. And all the crossed ones, like Q3 with Q4, they're all automatically satisfied. If you satisfy Q2 with, like we check it, then they're all satisfied. So what you do now, like this is very easy to apply for, like we managed to get like 20 charges in minutes. It's very computationally easy. And then now you have to make a choice, like you can put all the ones to 0, or you can make a choice that's efficient for you, but you have to sum the series you got for L6. So you got something, some results for L6, and you have to sum this series. And for this case, it's very easy, but I will soon show a different way. So the advantage of this for the cases we did so far was that we didn't get this crowd of solutions. The method seems for, like, we did very few cases so far, so I don't want to make a too strong claim. I don't know if this solves completely the problem with the dependent solutions. But so far it seems it already gives us something separate and nice. And the extra dependents are like all these free functions we have on the LAX. So they encode all the types of basis transformations and things you could do. In principle, they are there. So, and you can kind of choose these extra ones to have something nice or something that is more interesting, depending what you want. But depending on the model, it's not easy to sum the series. This is what we realized. It can be quite tricky to sum the series. So what we actually in practice did for all the examples, even in long range that I will explain later, was that if you put these extra ones to 0 from the beginning, you see that you have some elements that are very simple. And then especially for like here it doesn't make much sense because you would put them to 0, but in the long range it will make more sense. You can put all the simple ones there, and then you have just 1 or 2 complicated ones, or 4 or 5 depending if you have a larger ansatz or something. And just by computing the transfer matrix with the Hamiltonian, if you have few of them, you have something linear to solve. So these things that are extremely hard to sum, you just get them for free if you compute the transfer matrix with the Hamiltonian. So it's a nice trick, I think. And once you can find the LAX, you can just find the R matrix by solving RLL. It's linear, so you can do it quite quickly. So the advantages are that, so with these, you get a non-difference form R matrices for free, or like the difference form ones. You don't need to specify like to start with a Hamiltonian that's U dependent to get them. So automatically you should, if your model is regular, which was something we required at the beginning, you should be able to say if your model is integrable. So it seems more efficient in terms of not generating all these dependent solutions. But the thing we were quite happy about is that it's kind of easy to apply for long-range spin chains. With this trick of commuting with the Hamiltonian, so you solve a few orders, you see which ones you can put to 0, and then you can kind of do just commuting the transfer matrix with the Hamiltonian, you can get the rest. Okay, so yeah, just saying a few things, but that we all know. But yeah, in the context of Adscft for planar n equals to 4 at one loop, we know that the dilatation operator can be related to the integrable nearest neighbor spin chain. And at each order in perturbation theory, the interaction range of this Hamiltonian increases. So you have something like at one loop is nearest neighbor, 2 loops is like nearest next to nearest neighbor, and so on and so forth. And the full Hamiltonian will have like an infinite range. Like some framework, a framework to deal with this type of spin chains was put forward in 2008 for the charges. So they can perturbatively get the deformations for higher range. And it was later used to classify the integrable long-range deformations of the 6-vertex model. And what we would like to do now is we would like to apply this for the Hamiltonian of the SU2 sector in n equals to 4 spring Mills. So we'd like to see if we can get the R matrix and the LAX operator for like 2-3 loops. And we would like to see if the range 3 deformations that was on their paper, like for the charges, if they are Yang-Baxter integrable, in the sense if we can get the R matrix and the lax for them, and if all of them have like a lax and an R matrix, all the deformations. So these are the 2 questions I have to reply. We would like to reply. How much time do I have? I don't know if I'm going too fast or too slow. Okay, thank you. So to do this, we need one more ingredient. So last year, Tamás and Balázs put a very nice paper for that Tamás explained this morning as well, with these medium range spin chains. And they kind of realized that if you increase the dimension of the auxiliary space, you can use this to get long range deformation, like these longer range deformations in comparison with the nearest neighbor, like this finite long range. So for range 3, for example, if your physical space has dimension d of v, the dimension of the auxiliary space, you put the square. And then you can do many things, so we will use this here. And so for range R, what we do is like the dimension of the auxiliary space is the dimension of the physical space to the range -1. And we didn't consider wrapping, so if you're interested in wrapping, Tamás also explained many nice things this morning, and you can look a bit more in his paper, but we will avoid. So to avoid wrapping, we are always doing all the calculations for L at least equal to 2 times the range. Okay, so if we start with the Hamiltonian for SU2, we have this type of Hamiltonian, and so for integrability purposes, you can consider the second line is the same thing as the first line, since you are just shifting by identity. It's very easy to put back on their matrix this, so we are just considering the second case. So what we do is, again, we just follow our procedure with the expansion, and we'll put on the transfer matrix, again, like we did before, but now we will solve perturbatively to each order in G. So if we consider 2 loops, it's very, very easy because you just have one function to fix at the end. And we are requiring always these boundary conditions, so we kind of have all these regularity conditions are still here in the Hamiltonian. So you expect to recover the Hamiltonian here. So this case was very nice and simple to solve, and then we got both the lax and the R matrix for this 2 loop. The R matrix you can get just by perturbatively solving RLL. And then the next thing we decided to do was like try to do 3 loops. So these are the SU2 invariant objects you can put here. So we put these rows, and we apply the method. So we have to solve perturbatively up to G to the 4th. And we find some conditions, so these A's are in front of the sums here. We found some conditions on them. So here it's depending on A1 and A2, basically. And if you consider, so if it doesn't satisfy these, it's already not integrable, even perturbatively. And then considering that's symmetric, we have 2 deformations, but one is just the Q4. So it's something of range 4, what you have like is Q4, in this case, one of them. So it's one proper deformation. But I would like to highlight that we cannot put all the A's to 0. So even if you were not thinking in n equals to 4 super-Young mills or anything, this spin, if you truncate, this spin chain is not integrable. Like it's perturbatively integrable, but if you don't have the option to put all of them to 0. So if you have this range 3 deformation, this G squared, you have to keep putting. You have to put at least G to the 4th. And this kind of matches with the result by Anna and Tristan, where they found chaos when they look at they took up to 2 loops and they studied the model and they found chaos for this model. So it shows that the truncated model is not integrable. So we found explicitly the lax, and we found the R matrix, but there is no chance I can put it here. It's really, really huge. And because of that, so if you look here, you still have some lambdas. So you have that freedom I mentioned before that you keep. So here we kept this freedom, and you, in principle, you could think that they are completely free. For this case, they are not because of the boundary conditions. So if you expand on U like this, what you get some conditions you have to satisfy. And okay, I already mentioned the R. So we have both the lax and the R matrix up to 3 loops, and it would be nice to continue. It gets a bit harder computationally because since you need to keep increasing your auxiliary space, it becomes quite hard. But for these cases, we have the explicit formulas. And then the next question we'd like to solve is to answer is that if those deformations of those range 3 deformations computed for the charges, if they're all Yang-Baxter integrable. So we put this constant Hamiltonian, it's the same they have. We added the range 3 Hamiltonian here. And so since it's 6 vertex, the only condition we put is that the total Hamiltonian has to commute with the total spin operator. And we apply the method again. We put the expansion of the lax on the transfer matrix. We solve it perturbatively for so order 0 and 2 on G. And we found the lax and the R matrix. But the main result here is that all the range 3 deformations they have an R matrix associated to them. So all of them are Yang-Baxter integrable. And this is quite non-trivial, I think. Yeah, so it seems quite smooth to apply the method for long range. So there are quite a few things we think so we really can we can try to start to generate a perturbatively long range models that could be interesting. But I think also one of the main points for us is really this to be able to reply if the model is integrable or not. I think this is something we really wanted because we were really we were trying for a bit. So there are several future directions we could take. So we are really hopeful somewhere to find some functional way to write some closed formula for the lax and the R matrix. So if you just keep doing order by order, you find larger and larger objects. So we would like to find a way to factorize nicely these extra terms in a way that maybe we can see something, but we don't know yet. It would be nice to have this at all orders. Also now if we could apply to some physically interesting models, if anyone wants to try to get a long range, that could be interesting for many areas. And something that would be nice as well is in this paper with Anna and Kristen, they found that was chaotic when they truncated, but it was weakly chaotic in the sense that the crossover to the chaotic dynamics was it was lower than the generic chaotic model. So it seems that somehow the model remembers that that was integrable if you keep more. So something we're thinking is if you could take some simple models that like some nearest neighbor models that very simple, and try to get a few deformations and truncate and see if this is a behavior that's always there. Like if you do the same calculation, if it will be chaotic, weakly chaotic as well. So to see if this is something that was just an accident for n equals to 4 Superring Mills, or it's something that's a feature of these models that when you truncate the model kind of keeps some memory of what happened. And thank you. Yeah, that was.
Questions?
Can you please show Sutherland equation?
Yes.
So, assuming if I assume that H is known,
yes,
how many equations is there and how many variables?
All the ones that will be in your ansatz for R. So it depends how big is your model. Like you have a.
No, so let's say R is n by n matrix. Then it is.
Sorry?
So.
I didn't hear. It's a matrix, like they are matrix. So you start with some ansatz for the Hamiltonian, and let's say you know the Hamiltonian, so now you have a Hamiltonian, it's a matrix. You have to find the R, so you put an ansatz for the R, and you have to solve the equations to find all these elements on the. So you have a system of differential equations that they couple more and more depending on how crowded is your R matrix. So it becomes a bit harder if you.
So there are more equations than variables, right?
Yeah. That's true. There's more equation than variables. So, but what happened is that for each case we found a unique R that, and which makes sense, I think.
Further questions?
So parts of these long-range models that you look at, those that you can get by deformations with the higher boost operators are equivalent to inhomogeneous spin chains with inhomogeneities depending on the coupling constant, the deformation parameter. Maybe there could be some map between your Lux operators and Lux operators of inhomogeneous spin chains that exploits this relation. Yeah, it's probably more a comment than a question.
I'm not sure if at the very beginning I didn't hear what you. Sorry, could you repeat it, please?
Okay, these long-range models that you consider, parts of them, those that you get from deformations with these higher boost generators.
Yes.
They are equivalent to inhomogeneous spin chains where you have the inhomogeneities as functions of the coupling constant of this deformation parameter. And for those you can also write down Lux operators, right? So I'm wondering if your Lux operators somehow factorize into these inhomogeneous Lux operators that could maybe
it would be nice
be observed.
Yeah, I don't know, but it would be nice to see that.
Thank you.
So 2 questions from Rio Suzuki, but I think the second question was about inhomogeneities in the L operator, so I think it was answered. But the first question is this classification method doable for large dimensions?
Yes, you can apply for larger, like in some, do you mean just starting with a Hilbert space of higher dimension? I don't see why not. You could start with, the first or the second method? Actually.
So yes, there is a parenthesis here, spin S x x x with S greater than 1/2. The matrix dimensions of Limblandian is a square of Hamiltonian. This is Rio's question. Yeah. Is this classification method doable for large dimensions? Yes, but I cannot have a feedback.
For large Hilbert spaces, yes. So basically the conditions we put here were regularity, and that should reduce the Hamiltonian. So if it's in this class, I don't see why not. And the expansion, I also don't see why it would not. You're just expanding and putting on the. So I don't see why it would not work.
I see no further questions. We had quite a few questions along the way also. I think I'd like to close the session, but I would also like to thank Anna one more time.
Thank you.